Tell me guys, is it clear, audio video? Please tell me. So is audio video clear to everyone? Hello guys. I hope audio video clear, audio and video is clear. Yes, per unit वाला doubt ले लेंगे राहुल. Sure, per unit वाला topic मैं आज cover कराऊंगा. So thank you, and in today's session we'll start the marathon series for power system, and in this series there will be two sessions. So part 1 is on today's today we'll cover the part 1, and tomorrow we'll take the part 2. In part 1, what I'm going to teach you is about the transmission line, the line parameter like inductance and capacitance calculation, per unit system. Okay, so these three topics I'm going to cover it. Okay, so let's start the session, guys. Please share this session to everyone so that everybody can get benefited from this session, and please share it on your Telegram groups or whatever, on whatever group you are connected. So please share this session. Okay, so let's start the session, guys, and so this is my introduction, and I teach almost every subject, and right now I'm taking power system. Okay, this is Maha marathon series which is going on, and in this Maha marathon series now we have started the core subjects. Okay, so power system, and then machine, and then power electronics. Okay, so one by one we'll cover everything. So let me tell you guys, there is one mega workshop which will be on 15th of January, and it will be taken by Abhinav Negi sir, but this mega workshop is for GATE 2024 students. So please tell your friends, tell your juniors about this workshop, and tell them to attend this workshop so that they can get benefited, and there will be some tips for GATE 2024, how to be successful in GATE 2024 and how to start your preparation. Okay, and there is one more thing, that is if you want to avail some discount on the preparation courses, so you can get scholarship up to 90%. For that you have to register yourself. The link is given in the given below the video, so you can go there and you can register yourself there. Then you have to give some test. There will be a scholarship test for that, and then you can avail this offer. Okay, general aptitude marathon series marathon session is also coming soon, and it will be taken by Rakesh sir. So I hope you will enjoy this session also. And there is one more marathon session for mathematics is also coming soon, and soon the date will be announced, and you can join this session also. Okay, guys, so it's the time for the test series. So better you start giving the test series, and you join the test series now, and check your speed and accuracy. So BYJU'S exam prep is also providing you the test series, so you can join it. The cost is not that much high, and in this series there are so many tests. You can give the mock test, you can give the subject test, and you can check your preparation. Okay, so let's start the session, guys. Before starting the session, please subscribe if you haven't subscribed this channel. So please subscribe it, and like this session if you haven't liked it, and press the bell icon so that you get the notification whenever the session will be live. Okay, so let's start the session, guys. So first of all, I'll discuss about the calculation of the line inductance, how to calculate the line inductance. Now, one formula for line inductance is, I'm telling you only one formula. If you want to calculate the line inductance, then the formula will be 2 into 10 to the power minus 7 ln GMD over GMR. GMD over GMR. This is the universal formula, guys. Okay, everywhere you have to apply this formula. But you should know how to calculate GMR and how to calculate GMD. GMR is also called self GMD. Okay, GMR is also called self GMD. GMR is also called self GMD. Geometric mean distance. And GMD itself is, you can say, mutual distance. GMD is the mutual distance. GMR is the self distance. Now, what is the meaning of GMR and GMD and how to calculate it? Let's discuss about GMR first. Let's say I have 3 conductors like this, and they represent single phase. These conductors are of single phase. Okay, it's called bundling. Let's say there is a bundling of single phase conductors. So in a single phase wire there are actually 3 wires. Okay, and the distance between these wires is, let's say, D. This distance is D. and the radius of the wire is R. I want to calculate GMR of this system, okay? So GMR, how to calculate GMR, guys? GMR for this wire means self GMD. So what you can do is, let's say this is conductor 1, this is conductor 2, and this is conductor 3. So what you can do is, first you have to write the distance D11, and then D12, and then D13. Is it fine, guys? Because this conductor is for phase A. This is for phase A. So actually you are looking in phase A itself. There is no mutual distance here. Why? Because there is no phase B. If let's say there is phase B also, then only you can go with the mutual distances. Since there is no phase B, there is only one phase. If there is only one phase and these are the conductor for phase A, let's say. So in this case, you can only calculate GMR. So now how to calculate GMR? To calculate GMR, what you need to do is, you need to take the self distance D11, D12, D13. Now come to conductor number 2. So D21, D22 and D23. Now come to conductor number 3, D31, D32 and D33. Is it fine, guys? This way you can write the self GMD. Means this, it means the self distances. You have to multiply the self distances. Now what is this D11 and D22 and D33? What is the meaning of this? And moreover, since there are actually 9 terms, so you have to take 9th root. Okay, since there are 9 terms, you have to take 9th root. This way you can calculate GMR. So in GMR, what we need to do is, we need to calculate the self distances. You have to understand how to write these self distances. Okay, so now what we can do is, what is the D11, what is D22 and what is D33? D11 means 0.7788 R. 0.7788 R. Okay, and same, this will be equal to D22 and this will be equal to D33. So you have to remember like this. Is it fine? This is the self distance. We call it self distance. Okay, and D12 is this distance D, D13 is this distance D. Similarly for conductor 2, you can say 21, 22 and 23. Similarly for conductor 3, 31, 32 and 33. Okay, you can multiply all together and then take, since the terms are 9, you can take 9th root, and this way you can calculate GMR. So while calculating inductance, you should know how to calculate GMR and GMD. Now in this case, I'm not calculating GMD. Why? Because there is no phase B, there is only phase A. That's why there is no mutual distances. Okay, that's why I'm not going to calculate GMD. Whenever you need to calculate the inductance of some line, then obviously they will provide you some phase. Let's say there are 2 conductors. Okay, in this conductor you have I current, I coming out. Okay, and in this conductor I is going inside. Is it fine? And the radius is R, and the distance from center to center is D. This distance is D. Now I need to check about GMD and GMR. So look, this is phase A conductor and this is the return path. So if you want to calculate L1, inductance of this conductor, how to calculate the inductance of this conductor, guys? Tell me. If you want to calculate this inductance, you need to apply this formula. Okay, GMD upon GMR. Now what is GMR of this conductor? Since it is a single conductor, so GMR is, tell me, the GMR is R prime itself. That is equal to 0.7788 R. Because there is only one conductor. In previous case you have 3 conductors in a single phase. Now here you have only one conductor. Now how to calculate GMD? Now there is a mutual distance. There is a mutual distance between this conductor and this conductor. There is a mutual distance. So that mutual distance I call D. Okay. So this is my GMD. This is my GMR. So you can put the value and you can calculate the inductance. Is it fine, guys? So this way you can calculate the inductance. You can apply this formula and you can calculate the inductance value. I hope you understood it. So L1, inductance of this line will be equal to L2 inductance, because they have same radius. If they have different radius, then their inductance will be different. L1 for this will be different. L1 for this, L2 for this conductor will be different. Now since they have the same radius, you can say that L1 equal to L2 equal to 2 into 10 to the minus 7 ln GMD upon GMR. GMD is the mutual distance, which is d, and GMR is this r prime, radius into 0.7788. So just remember this formula, but you should know how to apply this formula. Okay, that's what I'm teaching you. Now let's come to the equilateral spacing line. Let's say you have these 3 conductors, and it's a 3-phase line. So this is phase A, let's say, this is phase B, and this is phase C, and they have equal distances. Okay, equilateral spacing is there. This is D, this is also D, okay, and this distance is also D, and the radius is R. The radius is R. For each conductor, the radius is R. Now we need to calculate GMD and GMR. So first of all, I need to calculate inductance of A phase, LA. So obviously LA will be equal to LB equal to LC. Now how to calculate LA? The formula is same, 2 into 10 to the minus 7 ln GMD upon GMR. So what I need to do is I need to calculate GMD and I need to calculate GMR. Now you can see that in one phase, in A phase, there is only one conductor. There is only one conductor in A phase. Okay, so GMR will be R prime itself. Okay, it's similar to this case. There is only one conductor, na? So that's why I have taken GMR equal to R prime. If in A phase, let's say there are 3 conductors like this, it's a if there is a bundling, then GMR will be like this. Okay, so you have to be careful. Now here only one conductor is there for phase A, so you can write like this. Now GMD, how to write GMD? To write the GMD, you have to take DAB, mutual distances you have to write. DAB, DBC, DCA. Okay, these are the mutual distances among them. Okay, these are the mutual distances between the conductors. Okay, DAB, DBC, DCA. These are the mutual distances. And since there are 3 terms, so you have to take cube root. Is it fine, guys? And since you have equal distances because there is equilateral spacing, so it will be D into D into D, D cube. Take the cube root of D cube, so it will become D itself. It will become D. Okay, so now you can put the value here, and LA will be GMD over GMR. I hope you understood it. So it's again very simple. It means the formula is very simple. The formula is you have to apply, you have to apply this formula everywhere, GMD over GMR, but you have to be careful how to calculate GMD and how to calculate GMR. Now, if the spacing is not equilateral, if there is no equilateral spacing, if the spacing is different, okay, unsymmetrical spacing is there. If unsymmetrical spacing is there, then inductance of each line will be different. Inductance of each line will be different, and it will create unbalancing in the line because every phase has different inductance. To make the inductance equal, what we do is we do transposition. It means by default we will take that if the whatever the 3-phase line is, there must be some transposition. What is the meaning of transposition? Tell me, guys. Transposition means for some distance the spacing are like this, A, B, C. Now after this distance you change the spacing. Okay, you change the spacing of these conductors, the phase conductor. Now A line is here, A phase is here, B phase is here, and C phase is here. Now after some distance, what you can do is again change the position. Again change the position like this. Okay, so this way you can change the position after equal distances. You can change the position of the conductor. This is called transposition. Now what is the advantage of this transposition? There are so many advantages of this transposition. The first advantage is line inductances will be equal. Okay, there will be a balancing in the line. Every line inductance will become equal, and if there is a communication line which is going in parallel, there will be no interference with the communication line. Okay, this is the advantage of transposition. So whenever you have unequal spacing, obviously if you are not doing the transposition, inductance of each phase will be different. That's why what we do is we do transposition. Advantage of transposition is you have equal inductance for each line. Now how to calculate the inductance? Again you have to apply the same formula, GMD over GMR. Now how to calculate GMR? GMR is the self distance. The radius is R. So the self distance GMR is R prime. Okay, so GMR is R prime. Is it fine, guys? GMR is R prime. Now how to calculate GMD? GMD is the mutual distance. So what you can do is you take these mutual distances, multiply them, and take the cube root. D12, D23, D31. Now this time these are not equal. Okay, so what you can do is you can take cube root of D12, D23, D31. Just remember this, and you can apply the formula. Okay, this will be the inductance of line A, and the same inductance will be for line B and line C, because there is a transposition. If it is not mentioned, that the line is transposed, then also you have to, I mean, by default you have to take that the line is transposed. Okay, so you have to be careful. Manoj Srivastava, sir, in single phase double line the inductance kaise nikale? Single phase double line. Okay, you means in single phase we have two lines, I mean two conductor for incoming and two conductor for outgoing. Are you saying like this? If you are saying like this, then again let's say this distance is D, this distance is D. It's called bundled conductor, and the spacing between these conductors is D. Okay, the spacing between these conductors is D, let's say. Now what you can do is, first of all, calculate GMR. GMR will be equal to, you have to calculate the self distance of these two conductors. So distance of this conductor with itself, we call it R prime, and distance of this conductor with this, that is called D. Okay, now distance of this conductor with itself, it is R prime. Okay, and distance of this conductor with this is D, and take fourth root since there are 4 terms. So this will be my GMR. Is it fine? This will be my GMR. Now what is GMD? GMD is D, because I'm assuming that D is much less than D. So what you can do is, you can assume that these conductors compared to this D, this is very small. So the mutual distance will become D itself. Okay, so the mutual distance GMD is D. GMD become D. So this way you can solve the question. Okay, I hope you understood it. The thing is, you have to apply this formula everywhere, but you should know how to calculate GMD and GMR. Once you get this idea, you can easily calculate the line inductances. Okay, so it's simple. So I told you, whenever you have unequal spacing, whenever the spacing is unsymmetrical, then what you can do is, by default you can take the line is transposed, and if the line is transposed, you can calculate GMR and GMD and you can apply the formula. Okay, now let's come to the bundled conductor. In bundled conductor, again, look, this is phase A, this is phase A, this is phase B, and this is phase C. So obviously there is unsymmetrical spacing. You can see that between A and B there is a distance D, between B and C there is again a distance, distance D. From this center to this center there is again distance D. This distance is also D, and between A and C the distance is 2D. So obviously the spacing between the conductors is not symmetrical, it is unsymmetrical spacing, and the conductor is bundled. In each phase you have 2 conductors. You must have seen the transmission line, overhead transmission line. In overhead transmission line there is not a single wire for A phase or B phase or C phase. Actually there are 2 wires going in side by side. Okay, so for A phase you have 2 wires, for B phase you have 2 wires, and for C phase you have 2 wires. It's called bundled conductor. Now how to calculate GMD and GMR here? So to calculate GMD and GMR, again it's very simple. Let me tell you guys. First of all, calculate GMD. So GMD is the mutual distance. Ideally the mutual distance would be, let's call it A and A prime, let's call it B, B prime, and let's call it C, C prime. Since I need to calculate the mutual distances, so I should write AB, AB prime, A prime B, A prime B prime, and then BC, BC prime, B prime C, B prime C prime, and then CA, CA prime, C prime A, and C prime A prime. This will be the mutual distance. Okay, but actually if you write like this, let me write it. Okay, so it will be AB, the mutual distance AB, and then AB prime, and then AC, A prime B, A prime B prime, A prime B prime. Okay, this is the mutual distance between 2 conductors A and B. Now what is the mutual distance between A and C? So that will be equal to AC, AC prime, A prime C, A prime C prime. Now what is the mutual distance between B and C? So that will be BC, BC prime, and then B prime C, B prime C prime. But it's a lengthy process. Obviously there are, you can see that 1, 2, 3, 4, and there are 12 terms. So you have to take 12th root. But the problem is, since D is assumed as very much less than D, you can say that this this distance, the distance between these two conductor of a single phase, this distance is much less than D. So what you can do is, you can say that this AB and this AB prime, they are approximately same as D. Okay, so this is D, this is D, this is okay, tell me guys, is it fine now? Is it fine now? Is it fine now? Tell me everyone. I think it's fine. Okay, let me repeat this again. Let me repeat this again. Okay, let me repeat this again. Okay, it's fine. Now, let me repeat this again. So I told you that I was calculating GMD. GMD means mutual distance. Mutual distance between AB, BC and CA. Now, if you look at this carefully, in this bundled situation, the mutual distance between A and B is AB, AB prime, AB, AB prime, and then A prime B, A prime B prime. This will be the mutual distance. Similarly, between B and C, you have BC, BC, BC prime, and then B prime C, B prime C prime. Similarly, you can calculate the mutual distance between C and A. So obviously, there are 12 terms, but since the assumption is D is much less than D, this distance is very small compared to this center to center distance. Compared to this distance, this D is very small. If this D is very small compared to this distance, so now stop looking these individual terms now, like AB and then AB prime. Okay, this distance will be D, this distance will be approximately D, this will also be D, this will also be D. So you are repeating again and again. So what you can do is, you can take only one time AB. Okay, the AB is approximately D now. Is it fine? The mutual distance between A and B, is, actually it should be AB, AB prime. But since AB and AB prime are approximately same, so what we can say is AB is D, and AB prime is D plus D, and then A prime B is D minus D, and then A prime B prime is D. Actually there are 4 terms, so you have to take 4th root. This will be the mutual distance between A and B. Now since D is much less than D, you can neglect it. You can neglect the small d. So the mutual distance between A and B came out to be D itself. Okay, is it fine? So now actually you have to write like this. But since you have taken this approximation, you can say that the mutual distance between A and B is D itself. Similarly, the mutual distance between B and C is again D itself, and the mutual distance between A and C is 2D. So GMD will be equal to, so if you want to calculate GMD will be equal to D into AB into BC into CA. Is it fine guys? And take the cube root. This way you can calculate GMD. I hope you understood it. Okay, I hope you understood it. So it's again very simple. It's again very simple. You can take the assumption and calculate the GMD. Now what is GMR here? Is it clear guys? Is there any doubt? Tell me, is there any doubt guys? Okay, okay, I have explained Raghuram. I have explained it. Is there any doubt guys? Tell me. I hope it is clear to everyone. Now let's come to GMR. How to calculate the GMR of conductor A? This is the conductor A. Now in conductor A we have to calculate the self distances. Self-conductor distances, okay? If you want to calculate self-conductor distances, then what you need to do is GMR. How to calculate GMR? To calculate GMR, what you need to do is, you need to write distance of A with A itself. We call it DAA or R prime, simply R prime. DAA prime, okay? And then DA prime A and DA prime A prime. Is it fine? This is the self distance. This is the self distance of conductor A. Is it fine guys? So this way you can write the self distance of conductor A. So it will be R prime into D and then D into R prime. Okay, so you can write it like this. There are actually 4 terms, so you have to take 4th root. So this AA will be R prime, AA prime will be D, and then A prime A will be D again, and then A prime is R prime again. Is it fine? This way you can calculate the self distance or GMR. Okay, this way you can calculate the GMR. I hope you understood this point. Okay, Now let's come to the next thing. Okay, you want me to solve one question? Yes, we can take one question. In last year also, they asked you one question. Let me take that question again, and then I will come to the parallel circuit three-phase line. So first, what I'm going to do is I'm going to take one question. Okay, so let's take one question which is asked in the last year, 2022. Okay, yes, you can also write root of dr prime, because if you look at this, it will be dr prime square of that, and you are taking fourth root. So obviously 2 will be cancelled, na? So you can say that it is the square root of dr prime. You can also write like this. There is no problem. I mean, you don't need to write this a prime, a prime, a prime, and a prime a again, because you have already taken this a prime, na? So why you are taking a prime a again? Since you have taken a prime and you are also taking a prime a, so you are repeating the same value. It doesn't matter. Even if you repeat the value, there is no problem. You have to count the number of terms, and you have to take since this distance a and a prime, they are repeating itself. They are again repeating. So you don't need to take this term again. But the problem is, let's say you have bundled conductor with one radius is greater than the other. Then what will be the GMR? What will be GMR? Tell me, guys. Let's say this is 2r, this radius is 2r, and this radius is r, and the center to center distance is d. Tell me, guys, what should be the GMR? Now, can you calculate the GMR? Now you cannot take only two terms. Because if you write, let's say this conductor is a and this conductor is a prime, and if you are writing like this, DAA, and then DAA prime, and then DA prime A, and then DA prime A prime, then it will be correct. Then it is correct. But if you are writing only two terms, because many students have crammed this formula. Many students think that, okay, this distance is d and the self distance is r prime, so they just only take two terms. Now you have to take four terms because the radius are not equal. Okay, so what will be my DAA? Tell me, guys. DAA, the self distance of conductor A, that will be 2r into 0.7788. Is it fine, guys? This is the self distance of conductor A. Now DAA prime is D. DA prime A, this is again D. A prime is R into 0.7788, that is R prime. Is it fine, guys? So you have to write and you have to take fourth root. This is 2R prime, this is R prime, and this is D and this is D. So be careful. You have to understand the complete formula. Short tricks will help you sometimes, but with the short tricks there are some constraint. I mean, this is correct only if you have equal radius of these two conductors. If you have different radius, then it will be problematic. Okay, so you have to be careful, guys. You have to be careful. You have to write it completely. Okay, and this way you can calculate it. Now if you look at the last year problem, let me see the last year problem, because last year it was asked in the gate question, in the gate paper. So let me write that problem. So the problem was 2022 1 mark problem was there. Let me write the problem. There were four conductors. There were four conductors like this. There were four conductors. Okay, gate 2022. Gate 2022. Okay, so it is asked the geometric mean radius. It means GMR is asked. We need to calculate GMR. Okay, and it is given that this radius is r. Wait a minute, this radius is given as r. We need to calculate the geometric GMR of this conductor. This is a bundled conductor. They have four, this conductor has four strands. There are four strands actually, and we need to calculate the GMR. Tell me, guys, what is the GMR? Can you calculate GMR? Do it fast. Do it fast. What is GMR? What is the self distance? GMR. Do it fast. What is self distance? Do it fast, guys. Do it fast. Do it fast. Tell me. Okay, let me solve this question. Okay, so let's call it 1. This is 2. This is 3. This is 4. So what you can do is you can write like this: D11, D12, D13, D14. Fine. Okay, I have written for 1. Now you can write D21, D22, D23, D24. Similarly, you can write for D31, but this is very lengthy process. Okay. If you look at this structure carefully, let me write it completely first. D41, D42, D43 and D44. This is my self GMD, and take the 16th root. But the problem is, this is very lengthy. This way is very lengthy. What you can do is, if you look at this conductor 1 carefully, whatever self distance of, whatever this distance, whatever this product is, this will also be the same product, this will also be the same product, this will also be the same product. So you don't need to write these, you are repeating these. Okay. You only write this and take the 4th root. You'll get the same answer. Because you are repeating the same thing. That's why the root order is also increasing. So don't repeat these same things. Whichever quantity is coming again, you can eliminate that. So only, you need to calculate only this and take the 4th root. Okay. Take the 4th root, D11, D12, D13 and D14, and take the 4th root. This will be my GMR. Is it fine, guys? Tell me, guys, is it clear? Is it clear? So what you can do is, what is D11? D11 is R prime. D11 is R prime. D12 is 2R. Now D13. D13 is again 2R. And D14. D14 is, you can apply this Pythagoras theorem. This is 2R, this is 2R. So 2R root 2. 2R root 2. Is it fine, guys? And take the 4th root. Okay. Now, this R prime is 0.7788R. Okay. Into, this will be 4R square, 2 root 2R. Is it fine, guys? And you need to take 4th root. So what you can take is, you can take this R common out, because R to the power 4 is there. So you can take R as out, and then you have to take 4th root of 0.7788 and then 4 and then 2 root 2. This way you can calculate it. Okay. So it's easy peasy. I hope you understood how to calculate GMD. Okay. I hope you understood how to calculate this GMR. So GMR is very easy to calculate. You have to take the self distances. Okay. Now let's come to the next case, parallel circuit 3-phase line. How to calculate GMD and GMR of parallel circuit 3-phase lines. Now it's very interesting. Parallel circuit 3-phase line. Okay. So let's take the GMD and GMR of parallel circuit 3-phase line. Okay. It's a bit different. It's little different. Why it is little different? Because look, in this case, what we have is, we have 2 parallel lines. If you look at the case, let me tell you. Just let me erase this. No? Okay, let me erase this, and let me erase this also. So now you have parallel circuit transmission line. What is the meaning of parallel circuit transmission line? Let's say you have the transmission. You have the. You must have seen this, na? This pole. Whenever you go outside, you'll see this type of pole. Okay, you'll see this type of pole. So on this pole, what you have is, you have actually 6 conductors like this. You have actually 6 conductors. Okay. Now in 6 conductor, 2 conductors are for phase A, and 2 conductors are for phase B, and 2 conductors are for phase C. Now the 2 conductors, we are not taking 2 conductors in parallel like we have done in bundling. In bundling, we have taken 2 conductors for phase A, 2 conductors for phase B, and 2 conductors for phase C in parallel. Okay. But now what we have done is, for phase A, what we are doing is, let's say this is phase A conductor, this is phase B conductor, and this is phase C conductor. So on this side, this must be phase A. Let's call it A prime, we call it B prime, and we call it C prime. Now what is the advantage of this? What is the advantage of this? Why we take parallel circuit transmission line? Why we take parallel? We call it parallel circuit transmission line. Why we are taking parallel circuit transmission line? Tell me, guys. The advantage of this is, this way we can minimize the inductance value. If the inductance can be minimized, the line reactance, per phase reactance can be minimized. Per phase reactance can be minimized. If the per phase reactance is minimized, then the power flow can be increased. Okay, let's say this size is delta. So the active power flow will be Vt into EF by XS sine delta. So you can see that if your x is less, if your xs is less, let's say, then you can say that the power flow can be increased. That's why our motive is to decrease x, line reactance. To decrease the line reactance, we can decrease the line inductance. If the line inductance can be decreased, now how to decrease the line inductance? One way is to do the bundling. If you are bundling, then what happens is, it will be 2 into 10 to the power minus 7 ln GMD over GMR. Now you can see that with the help of bundling, this GMR can be increased. If this GMR can be increased, that's why this L can be decreased. Conductor inductance of phase A or phase B or phase C. Now there is one more way to decrease the inductance, and that way is use the parallel circuit transmission line. But the problem here is, the problem in this parallel circuit transmission line is, there is unequal spacing between the conductors. So what we do is, we will take transposition. What is the meaning of transposition? Let's say for some distance A, B, C are like this. So obviously after some distance you have to change the position. You have to change the position, and then after some distance you have to again change the position. You have to again change the position. Is it fine, guys? This way you have to take transposition. So if I take the transposition, in position 1 you have A, B, C like this. A, B, C, and this is A prime, this is B prime, and this is C prime. This is my position 1. Now in position 2, cyclically you change na. So you change them cyclically, like this. This is A now, this is B now, and this is C now. And with these conductors, you can say that this was A prime, this was B prime, this was C prime. So it will become A prime, it will become B prime, and it will become C prime. Now this is position 1. This is position 1. Okay. This is position 1. This is position 2. This is position 2. And this is position 3. We can write it like this. This is again position number 3. Now if you look at this carefully, let me first write the position now. This is A, this is B, this is C. I have further this A was replaced like this, and then A is again goes down. Okay. And then B is this and C is this. Similarly, here this was A prime. So I have replaced this with A prime. It will become B prime, it will become C prime. If you look at this carefully, this is my position 3. This is my position 3. Now you can see that the distance between AA prime and CC prime is higher now. Okay. If you want to calculate the GMD, in GMD we use self distances. So now you can see that the distance between AA prime or AA prime or maybe CC prime, within two conductors, if you look at this, two phases, A or C, any two phase, let's say take A and C, the distance between A conductor is now higher. So GMR will be much lesser here. Okay, GMR will be much higher here. If GMR is much higher, then you can say inductance will be much lower. So this is the way to decrease the line inductance. Now in any position, if you look at this position also, these conductors CC and BB here, they are at the maximum distance. Similarly, if in this case you look at this carefully, B conductor and AA conductor are just opposite to each other. Okay, so this is the way to decrease the line inductance. Now the question is how to calculate GMD and GMR, because we need to calculate the line inductance. To calculate the line inductance, we must know the GMD and GMR. Okay, so let me tell you guys how to calculate GMD and GMR. First of all, GMR. Now it's a bit tricky. How to calculate GMR? Self distance. So self distance I am writing for conductor A. Okay, I am writing for conductor A. Okay, so if you are looking at the self distance of conductor A, then it will be AA, DAA, AA prime, right? AA into AA prime. But let me tell you guys, AA is the self distance and AA prime is this distance. But if you look at this carefully, in the position 2, this AA prime distance is somewhat different, and in position 3, this AA prime is somewhat different. So what you can do is, you can write this for position 1 also, and the same quantity AA into AA prime for position 2, because it will be different, this product will be different, and you can write AA into AA prime for position 3. Is it fine, guys? This is for position 3. Since the position is changing, is it fine? So the self distance is changing between AA and AA prime, between A and A prime, because self means you have to calculate the self GMD. Self GMD means internal distance you have to calculate. It means for phase A, there are two conductors. So you have to calculate the internal distance between these two conductors. We call it self distance. Okay. So if you look at this carefully, in position A, the distance between A and A prime is different here. Here the A and A prime is different, and here A and A prime distance is different. So what you can do is, you can calculate AA and AA prime for position 1, AA and AA prime for position 2, and AA and AA prime for position 3. Multiply them and take the 6th root. Is it fine? This we call GMR. I hope it is clear to everyone. Tell me guys, is it clear? Have you understood this? Now in many books, what they write is AA into AA prime. Now they write BB into BB prime. In this position only, they calculate the GMD, or they calculate GMR from position 1 itself. How they calculate? They write AA and AA prime into BB and BB prime. Now look, this BB and BB prime is same as this AA and AA prime. Is it fine? So what they are doing is, they are saying that AA and AA prime in position 2 is same as BB and BB prime in position 1. So in place of this, they are not going on position 2. They are standing at position 1 and they are writing this GMR as, so don't be confused. They write AA prime, AA into AA prime, and then BB into BB prime. Actually in position 1, BB into BB prime is same as this distance, which we have written in for position 2. That same distance came out in position 1 for B. And similarly, if you write CC and CC prime in position 1, this is for position 1, this is also for position 1, this is also for position 1. Now, this distance for position 1 is same as AA and AA prime for position 2. This distance in position 1, CC and CC prime, is same as the distance between AA and AA prime in position 3. Is it fine, guys? So in some books, they write like this. It is again correct. What they are doing is, they are looking at only position 1. They are looking at the position 1 only. Okay. And then they are calculating this GMR like this. You don't need to do this because you are taking self distances. So why you are looking at phase B? You are calculating the self distance of the conductor phase A only. So if you are looking the self distance of phase A only, then look at the conductor of phase A only. Phase A for position 1, phase A for position, phase A distance for position 2, and phase A distance for position 3. You can multiply them. Is it fine? I hope it is clear to everyone. Tell me guys, say yes or no. Have you understood this point? Tell me guys, how to calculate GMR here in parallel circuit transmission line. Is it clear everyone? Tell me, have you understood this? Say yes or no. Tell me guys, have you understood it? Say yes or no. How to calculate the GMR? Tell me everyone. I want your reply. Have you understood it? So don't be confused. In some books it is written like this. So this distance for position 1 is same as this distance for position 2. Okay. And this distance for position 1 is same as this distance in position 3. So be careful guys. Be careful. You can write for conductor A only. Now, okay, I told you about GMR. You can calculate GMR like this. Now you may say, sir, but there is transposition in this case also, no? Let's say the conductor is bundled. Here also you do the transposition. So why you are not looking position 1 and position 2 and position 3? Okay, in this case, why I am not looking position 1 and position 2 and position 3? Because look, this is for conductor A. If A is replaced here or A is replaced here, then the distance between AA prime will remain same, whether the conductor is at this position or this position or this position. The distance between AA prime will remain same. That's why I am looking only this AA prime. But in this case, if you are changing the position, then the distance between AA prime will change. Okay, then the distance between AA prime will change. Remember, that's why I am writing all these three positions. Okay, that's why I am writing all these three positions. And in bundled conductor, I was not writing like this, because in bundled conductor, the distance between AA prime, let's say this is position. In position 1, AA prime is here. In position 2, AA prime is here. In position 3, AA prime is here. If you look at the self distance between AA prime, it will remain same. Whether you take in position 1 or whether you take in position 2 or position 3. Is it fine, guys? I hope it is clear to everyone. So be careful while writing the GMR of this conductor in parallel circuit transmission line. Now, how to calculate GMD? So we have calculated GMR. Now look at the GMD. Now look at the GMD. GMD is the mutual distance. How to calculate the GMD now? To calculate the GMD, what we can do is, now how to calculate GMD? Okay, let's see how to calculate GMD. GMD means mutual distance. Okay, we have to calculate GMD, mutual distance. Now tell me how to write the GMD. GMD means the mutual distance. Now here in this case, you have to write AB AC, A prime B, A prime B, A prime B, and A prime C. Okay. So with conductor A, I have calculated the mutual distances. The conductor A, I have calculated the mutual distances. Now for conductor B. Now for conductor B, you have BA, BC, and then B prime A, B prime C. Is it fine, guys? So we have taken with conductor B, BA, BC, and then B prime A, B prime C. Okay? Is it fine, guys? Tell me. Is it clear? I have taken all the mutual distances. Now similarly for phase C. So it will be BCA, it will be CA, yes, it is CA prime, CB prime. Is it clear, guys? So what we have done is, we have taken the mutual distance of A with B and A with C. Similarly, B with A and B with C. Similarly, C with A and C with B. But there are not only A, B, C. There are actually A prime, B prime, C prime are also there. So what we can do is, A prime B, A prime C, A prime B prime, A prime C prime. Is it fine? Similarly, B prime A, because actually in A, there are A and A prime, two conductors are there, na? So we have to write the mutual distance of A with B and C, B prime and C prime. Okay, then we have to write the mutual distance of conductor B with A with C, with A prime, C prime. Now C with A and C with B and C with A prime and C with B prime. Now you have to write the mutual distance of A prime with B prime and C prime, and B and C. So A prime B, A prime C, A prime B prime, A prime C prime. Similarly, B prime A, B prime C, B prime A prime, B prime C prime. Similarly, C prime A, C prime B, C prime B, C prime A, C prime A prime, C prime B, C prime B prime. Okay, these are the mutual distances, guys. How many terms are there? 4, 12, and there are 24 terms actually. Okay, so you have to take 24. Now let me tell you guys, this lower product and this upper product will be same. So that's why you don't need to write this. You take only these 12 terms and take the 12th root. Okay, this will give you the GMD. I don't know how many of you have understood it. How to calculate the mutual distances? To calculate the mutual distances, you have to calculate A with B and C. Since there are two A's, A and A prime. So what I need to do is, I need to write all the distances like AB, AC, then A prime, AB prime, AC prime. So this is the A distance with other conductors. Distance of conductor A with other conductors, B and C. So in B and C, you have to write AB, AC, AB prime, AC prime. Now you have to write also the conductor A prime. Nah? There is also A prime conductor. So A prime should also be written like A prime B, A prime C, A prime B prime, A prime C prime. Okay, then write for B. Okay, then write for B and B prime. Write for C and C prime. Now we can see that this will be the repetition of the upper product. I mean, whatever this product, you will get the same product here. That's why I'm eliminating this and I'm taking only this side distance with this. Okay, and there is 12th root. This way you can write the mutual GMD. I hope you understood it. How to calculate the GMD and GMR. Once you get this GMD and GMR now you can put the formula and you can calculate the line inductance. It's simple. It's easy peasy. So you should know how to calculate GMD and GMR. Okay. So this was about the line inductance. Now let's go to line capacitance. Let's go to the line capacitance. In line capacitance, again, the capacitance of phase conductor with the neutral point, the formula we use is same. That is 2 pi epsilon upon ln GMD over GMR. But now the GMR is somewhat different. We will use this formula and this will be the capacitance of phase conductor A with neutral. This is the formula. Okay. Sir, how to calculate GMR in n conductor or in circular? I told you, if there are n conductors in circle, let's say there are n conductors in circle. Okay. What you can do is, there are, let's say, n conductor in circle. You take one conductor only. One with 1, one with 2, one with 3, one with 4, one with 5, and write like this. Okay. You don't need to write other. You don't need to write other. You don't need to go to 2 now. Because whatever the distance of 1 with all the conductors, the same distances will be 2 with all the conductors. So you can write for D11, D12 up to D1n. Okay. And take the nth root. Simple. This will be my GMR. Why you have not written D21, 22? Because if you write D21, this D21 is this distance, D22 is self distance, D23 is this, D24 is this, D25 is this. So you are repeating all the distances which you have written for conductor 1. All the distances are repeating for conductor 2. So why you are repeating here? The number of terms you are repeating, the same number of times you have to take the root. So don't repeat. Just write for conductor 1 and take the nth root. Simple. Is it fine? Praneeth, tell me guys. I hope it is clear. Okay. Now let's come for capacitance calculation. In capacitance calculation, what you do is, the capacitance of phase conductor with neutral point is, 2 pi epsilon upon ln GMD over GMR. Now in this GMR, whenever you write, let's say there are two bundling. Okay, there are this is phase A and this distance is D, and there is a bundling of conductors. Now in calculating GMR, previously what we have done is, in inductance calculation, we have written this GMR as R prime into D. But in case of capacitance calculation, we don't take R prime. We take R only. R into D. Just remember this point. Nothing will change. Okay. Nothing will change. Only R will change. R prime can be replaced with R. Everything will remain same. Okay. So you can say it's a modified GMR. Okay. So, and GMD will remain same. GMD will remain same. So this way you can write the capacitance of a phase conductor with neutral. Okay. Now let's say this is a single phase line. Oh, here you have positive current, here you have negative current, and the capacitance between these two lines is CAB. But we are not interested in CAB. We are interested in, let's say, here you have positive potential, here you have negative potential. So obviously this point we'll call neutral point. Okay, we call this point as neutral point. So with respect to neutral point, we have CAN and this is CBN. How to calculate this CAN and CBN? CAN or CBN will be 2 pi epsilon divided by ln GMD over GMR. What is GMD? GMD between these two conductors is D. Okay, and GMR is R itself. Okay, so D upon R, farad per meter. This way you can calculate the capacitance. Okay. Sir, but only the radius of bigger circle is given. No distance mentioned. That's a beautiful thing. You have to apply the geometry. You have to apply the geometry concept. Okay. You have to apply the geometry concept and then you have to calculate this distance. You can calculate the angle part. Na? Using the angle concept, you can calculate this distance. This is very lengthy problem. You have to check what is this distance, what is this distance, and what is this distance. In sine or cosine terms, it will come. Okay. So you have to calculate this. I have already calculated this. You can check my DPP for power system 1. I mean DPP 1 for power system. You can check on Google. I mean on WhatsApp. Not on WhatsApp. On YouTube. DPP 1 power system by Asu Jangra. Okay. By Asu Jangra. Okay. You will get this, and in that I have taken the same problem. I have taken the same problem and I have calculated this question. So please go and watch it. Okay, you'll understand how to calculate these distances. But I have told you the method. Okay, now you have to apply the geometry. Now let's come to the capacitance problem. So I told you, you can write CN. How to write CN, guys? Again the same thing. 2 pi epsilon divided by ln GMD over GMR. Let's come to the three-phase circuit. Now in three-phase circuit, we need to calculate the capacitance of three-phase line with equilateral spacing. If the spacing is equilateral, then you can calculate the capacitance of conductor A with neutral. Okay, let's call it neutral point. This is the neutral point. This is A. So between this A and neutral point, this is the B and neutral, this is C and neutral. So now you can calculate the capacitance Cn as 2 pi epsilon ln GMD over GMR. Since the spacing is equal, so the GMD will be equal to D12, D13, D31. This is the mutual distance, guys. This is the mutual distance. Since these distances are equal, so D, this is the D cube, and you have to take cube root of that. So the GMD came out to be D itself, okay? D itself. And GMR is R. Okay, this way you can put the formula and you can calculate the line capacitance. But this is phase capacitance with the neutral, with respect to neutral, okay? Between the phase and the neutral, this is the capacitance of the line. Similarly, if you have unequal spacing, let's say you have unequal spacing, only the GMD will change. This will be the cube root. This will be the cube root. D12, D23, D31, only the GMD will change and the entire formula will remain same. We call it CAN or CBN or CCN. Okay, I think it's easy peasy. Everything remains same. Now let's come to capacitance effect. I mean the effect of earth. How to look at the effect of earth? It's again simple. I'm not going into the derivation. The only thing is, look, these distances are D12, D31 and D23. They are unequal spacing. If there is no effect of the earth, then this will be the capacitance 2 pi epsilon divided by ln cube root of this divided by R. Because of the earth effect, there is some image charges, and this denominator will decrease. This denominator will decrease by this factor. So ln H12, H23, H31. What is this H12, H23? H12 is this distance, because this is 1. This is H12, this is H13, and there is H31. H31 is H31. What is H31? This is H12, 13, 1 to 2, 3. Okay, 2, 3 I have to write, na? 2, 3. What is 2, 3, guys? This is H23. Okay. 1, 2, H12. This is H1, H2, and H3. Vertical distance are H1, H2, H3. Okay, and then H12. H12 is this. H23. H23 is, what is H23? This is 2. This is, wait a minute. 2, 3. What is 2, 3? H23. H23 is this distance. Okay. This distance is H23. Okay. So you have to remember this formula. They will not ask you because it will never ask. But anyway, you have to be careful about this formula. But the final result you have to understand. If you are looking the effect of the earth, then you can say that the denominator has decreased. If the denominator has decreased, the capacitance the phase capacitance will increase. The phase capacitance will increase. If the phase capacitance will increase, the reactance will decrease. Okay, the reactance will decrease. Is it fine, guys? The capacitive reactance will decrease. The charging current will also, look at the charging current. The charging current will increase. Because these capacitances are in parallel. These capacitances are shown in parallel. So if the capacitance of the phase with neutral, let's say they are decreased. If the capacitance is decreased, wait a minute. If the capacitance value is decreased, then you can see that the reactance get increased. It's not correct. Actually, it's 1 by j omega c. Wait a minute, guys. Why it is not working? Okay. 1 by j omega c. So now you can see that if this capacitance get decreased due to earth effect, if the capacitance get decreased, what will happen is this overall factor will increase. It means this reactances will increase. If these reactances are getting increased, what will happen is the charging current will decrease. Okay, the charging current will decrease. So you have to be careful about this. So you can analyze the effect of earth. Now let's say the height is very large. If the height is very large, then this product will be approximately equal to this, and this will be cancelled. Okay, this will become 1, ln 1 is 0. Only answer is this, 2 pi epsilon divided by ln d12, d23, d31 upon r. Okay, so you remember this. Okay, effect of earth on the capacitance of three-phase line. So just remember this formula. Okay, now let's come to the bundled conductor. In case of bundled conductor, again you have to write the GMD. What is GMD? GMD is AB distance is this, BC distance is this, and CA distance is 2D, because I am taking D much less than D. Okay, so what you can do is GMD is D into 2D into D and take the cube root. What is the GMR? GMR is R into D. It's not R prime into D, it's R into D. Okay, so this way you can calculate CAN. Okay, CAN. Now parallel circuit transfer line. The parallel circuit transfer line, again you can apply the same formula, 2 pi epsilon upon GMD or GMR. Now how to calculate GMR? We have already done that. In parallel circuit transmission line, what is GMR? How to calculate GMR? Let's come back. In parallel circuit transmission line, GMR. This is my GMR, but in place of AA, don't take R prime here. You have to take R here. Okay. So be careful while writing the GMR of parallel circuit transmission line, and the GMD will remain same. I hope it is clear to everyone. Now it's time for the transmission line. I told you how to calculate the capacitance and the inductance. You need to remember only two formulas, and you need to understand how to apply these two formulas. If you know how to apply these formulas, then you can easily calculate the values. Now let's come to transmission line. So there are actually three types of transmission line. We categorize the transmission line in three parts. What are those? One is short transmission line, one is medium transmission line, and the third one is long transmission line. Okay, now what is the criteria which we call short and medium and then long? Actually it depends on the wavelength. If the length of the line is much less than wavelength, half of the wavelength, then we call it short. If length is comparable with lambda by 2, we call it long transmission line. Okay, and if length is not comparable, I mean in between, you can say that line is medium. Let's say for 50 hertz, try to calculate wavelength. Wavelength came out to be 3 into 10 to the power 8 meter divided by 50, so it will be 6,000 kilometer. So 6,000 kilometer is the wavelength. Now lambda by 2 came out to be 3,000. 3,000 kilometer is lambda by 2. Now if the length is much less than this, it means approximately 10 times less. It means if length is approximately less than 300, we call it medium or short. It will lie in this category, medium. If let's say the length is less than 100 kilometer, we call it short transmission line. This is an approximate idea. In some book you will find different value. Okay, so if less than 100, the line fall in this category. If 100 to 300, it will become medium, and if it is comparable to, I mean if more than 300, then the line length will become comparable to lambda by 2. It will become comparable to lambda by 2, and we call it long transmission line. Okay, so first of all you have to understand how to check which one is short and medium and long. Okay, now first of all look at the short transmission line. In short transmission line, actually there are 4 parameters of the line. There are 4 parameters. There is R, L, C and G. What are those? R is called resistance of the line per unit length. Resistance per unit length. L is called capacitance of the line per unit length. Capacitance per unit length. Okay, sorry, inductance per unit length. And C is the capacitance per unit length. I have told you how to calculate these. Okay. What is G? G is called conductance per unit length. G represent the leakage charge. The charge which is leaking. Okay. The charge which is leaking. We call it leakage charge. Okay. C represent the line capacitance. Okay. L represent the line inductance, and R represent the line resistance. Now, if you want to look at this capacitance has to be between these two conductors. Okay. Wherever there is a potential difference between the conductor, you have to show the capacitance in between. Okay. So capacitance will be shown in between. Similarly, G means it is the leakage charge effect. So leakage charge is again between these two conductors. So you have to represent this G again between these two conductors. Now R is a series phenomena. R is the resistance of this line. That's why you have to show it in series. Similarly, L is again line inductance. You have to show in series. Is it fine, guys? So you can say that R and L can be represented in series and C and G can be represented in parallel. So be careful, guys. Now, first of all, let's look at the short transmission line. In short transmission line, we ignore C and G. Why? Because if you look at the capacitance value, capacitance per unit length, it will be very small. Capacitance will be very small. If the capacitance is very small, then the reactance, capacitive reactance will be very large. So you can ignore it. You can ignore the entire line capacitance because capacitance per unit length is very small. Capacitance per unit length, per meter or per kilometer is very small. Even if you multiply the line distance with it to calculate the total capacitance of the line, since the line length is very small, the entire line capacitance will also be very small. Okay, that's why you can ignore this case. And similarly, in short transmission line, the leakage charge is again negligible. So you can say that G can also be neglected. So the short transmission line can be represented like this. Short transmission line can be represented like this. Okay, only R and L will be there. Is it fine, guys? In short transmission line, only R and L will be there. You have to show R and L. Okay, so this is called short transmission line. Okay, we don't show capacitance and leakage reactance here. So this will be the model of the short. We have used lumped model. We have done the lumping. Okay, this is the lumped model. So you can also show it like this: R and J omega L. This is my short transmission line representation. Now the question is, what is the ABCD parameter of this line? How to calculate the transmission parameter of this line? What is the transmission parameter? You must have studied in the network theory. Transmission parameter are, you have to show Vs and Is, sending end voltage and sending end current, in terms of receiving end voltage and receiving end current, Vr and Ir. Okay, you have to show sending end voltage and sending end current in terms of receiving end voltage and receiving end current. Now, if you look at this line, you can say that Vs will be equal to Vr plus this current is IR. So this current is also IR into Z. IR into Z. So we have calculated Vs in terms of Vr and IR. So this coefficient will be 1, this coefficient will be Z. And we know that Is is equal to IR because it's a series circuit. So Is equal to IR. So now you can see that Is equal to IR only, 0, 1 you have to write. Is it fine? So these are the transmission line parameter, ABCD parameter, okay, ABCD parameter. These are very important. Important in calculation of power flow and important in calculation of voltage regulation. Okay, I'll tell you why. But before that, let me tell you guys, the transmission line, every transmission line will be symmetric and reciprocal. Remember this point. Every transmission line will be symmetric and reciprocal. Whether you take short transmission line, medium or long transmission line, it will be symmetric. Symmetric means, tell me the meaning of symmetric. Symmetric means A must be equal to D. And reciprocal means, tell me guys, reciprocal means AD minus BC must be equal to 1. So it must satisfy whether the line is short, long or medium. Now you can see that A equal to D and AD minus BC is 1. Okay. So every transmission line will satisfy this condition. So we have calculated ABCD. Now the question is, using this ABCD, you can calculate the voltage regulation. What is the expression for voltage regulation? Voltage regulation is V receiving end, no load. You have to look at this receiving end voltage at no load minus V receiving at full load, whatever the load is. Let's say the load is full load, rated load is there. It's not necessary that you connect rated load, whatever load is there. Okay. So V no load minus V load upon V load. Okay, this will be the formula for voltage regulation. If the load is full load, let's say you have applied rated load, then you have to take rated load here. Is it fine? Or rated or full load you can say. So VR no load minus VR full load upon VR full load. Now the question is how to calculate this VR no load. At this receiving end, how to calculate this VR no load? Obviously, VR no load, if there is no current here, this voltage must be equal to Vs only. You can easily find it. Okay. You can easily find it in this expression. But in medium transmission line or long transmission line, it will be difficult to find no load voltage. But if you know the ABCD parameter, then you can say that Vs equal to AVR plus BIR. We know that. No load means there is no IR. At no load, IR is 0. We know that IR is 0. If IR is 0, you can say that Vs equal to AVR. Vs equal to AVR. So from here you can calculate receiving end voltage at no load. Receiving end voltage at no load will be equal to Vs by A. Is it clear, guys? Receiving end voltage at no load will be Vs by A. So what you can do is, if you know the sending end voltage and if you know the parameter, if you know the ABCD parameter of the line, at least the A you should know. Because if you know A and B now, if you know A and B, then C and D can be calculated directly. If you know these two parameters only, these two parameters you can calculate from these two conditions. Because you know that in every transmission line, A must be equal to D. If you know this A, D will also be known to us. If you know A, B, C, A, B, D, then C can be calculated using the reciprocal condition. I hope it is clear to everyone. Is it fine, guys? So what we can do is, at no load, we know that IR is 0. If IR is 0, this relation will become like this. And you can calculate VR at no load. So VR at no load is Vs by A. So what you can do is, you can replace this VR no load as Vs by A mode minus VR full load. Take the magnitude and VR full load. So this way you can calculate the voltage regulation into 100. You will get the percentage voltage regulation. Is it fine, guys? I hope you understood it. Okay. So in short transmission line, you can calculate A, B, C, D, and you can calculate the voltage regulation also. It's similar to transformer. If you know the transformer diagram, if you know the transformer equivalent diagram was like this: R equivalent and X equivalent. Okay, if you remember, the secondary side referred diagram for the transformer is E2, this is JX equivalent 2, and this is R equivalent 2. Okay, and you need to calculate the voltage regulation. The circuit is same now. The same circuit is used here. On this side you have the voltage Vs, this is R and X, and this side is VR. So same circuit is used. So whatever the formula you have applied in transformer, the same formula will be applicable here. Now what was the formula in transformer? Tell me, guys. What was the formula for voltage regulation in transformer? If you remember, the formula for voltage regulation in transformer, it was epsilon R cos theta z plus epsilon X sin theta z. I suppose this was the formula. I don't remember it. This was the per unit value of R equivalent. This was the per unit value of X equivalent. Okay. So this way you have calculated the voltage regulation. Okay. I don't know whether it is correct or not, but this was the formula. I can derive it. I can take it and I can calculate like this. No load voltage is E2. No load voltage is E2. And the load voltage, you can calculate that load current is IL. So you take E2 minus this drop, you will get this V2. Okay. So this way you can calculate like this. I hope you understood it. Anyway, so I told you how to find these ABCD parameter and how to calculate the voltage regulation. Okay. Now let's come to the power flow. How to calculate the active power at the receiving end and reactive power at the receiving end. Okay. Now I want to tell you about the power flow. What is the power flow in every type of transmission line? Because if you have calculated ABCD, then you are not limited to short transmission line. Because ABCD parameter will exist for all the lines, na? Short, medium and long. If you know the ABCD parameter, and if you calculate receiving and active power and receiving and reactive power in terms of ABCD parameter, then this is valid for every type of line, na? Because ABCD are the generalized parameter. You can calculate ABCD for every type of line, whether it is short or medium or long. Once you get this ABCD parameter, you can calculate receiving and active power and receiving and reactive power in terms of ABCD parameter. Now let's say the line is medium and you want to calculate active power at the receiving end and the reactive power at the receiving end. You can put the ABCD of the medium transmission line. You can get the active and reactive power of the medium transmission. Let me tell you how to calculate active and reactive power for the medium transmission line and short transmission line. Okay, so this is A, B. This should be B. It cannot be D. It should be B. It should be B. This is C and D. Okay. Now we know that for any transmission line, these are the ABCD parameter. Let's say ABCD parameter. So if I open the VS and IS equation, it will be like this: AVR plus BIR, CVR plus DIR. From this relation, from this upper relation, I can calculate IR. Receiving end current I can calculate. Okay. So the receiving end current will be VS minus AVR Vs minus AVR divided by B. This should be B. Okay, this should be B. Is it fine, guys? So what you can do is you can say IR is equal to Vs minus AVR upon B. Now these A, B, C, D are the complex numbers. They are the complex numbers. So what I can do is I can write them with their angle. Magnitude is A, angle is alpha. Magnitude is B, angle is beta. Okay, I don't want to write C and D because C and D are not important for me. So now, and I'm saying that angle of VR is 0. Let's say that receiving end voltage angle is 0 and sending end voltage is, let's say, delta. Okay, sending end voltage is, let's say, delta. The line is like this. This is my line and this is the receiving end, this is the sending end. At receiving end, the voltage is VR angle 0 and the current is, let's say, current is lagging. Current is lagging by theta. Current is lagging by theta. Okay, IR is lagging by theta. So what we have done is we have calculated IR. Okay, and remember this Vs is at an angle delta, let's say. Okay, Vs is at an angle delta. Now IR came out to be this. Now if I want to calculate this in terms of magnitude and phase, it will be Vs magnitude divided by B magnitude, and the angle will be, what is the angle of Vs? Vs angle is delta and the angle of B is beta. So it will be delta minus beta minus magnitude of A, magnitude of VR divided by magnitude of B and the angle. What is angle? Angle of A is alpha, angle of VR is 0. So angle of AVR is alpha minus beta. So alpha minus beta will be the angle here. Okay, so this is my IR, guys. We have calculated IR. Once you get this IR, what I need to do is for active power at the receiving end, what I need to do is I have to take VR, multiply by IR conjugate and take the real part of that. You'll get the active power at the receiving end. So active power at the receiving end will be, let me write the active power now. If you want to write the active power at the receiving end, so PR will be equal to VR into IR conjugate. If you take the conjugate of IR, this will be minus, this will be plus, and this will be minus, this will be plus. Is it fine, guys? If you take the conjugate, angle will be, the sign of the angle will change. Okay, so this is minus alpha and plus beta, and this is minus delta plus beta. So okay, now let's come to this VR and IR conjugate and the real part. So VR into IR conjugate is, let's first calculate VR into IR conjugate. That will be equal to, since we know that angle of VR is 0, okay, so what we can do is we can write like this: VR magnitude into Vs magnitude upon B magnitude, and angle is, tell me guys, angle is beta minus delta. Now you'll say, sir, but you have to add the angle of VR. Now angle of VR is 0, yaar. So you don't need to add it. Minus magnitude of A, VR mod square divided by magnitude of B, and the angle is beta minus alpha. Okay, this will be VR IR conjugate. Now you need to take active power. You need to take real part of this. So if you need to take real part of this, what you can do is you can take the real part of this will be, you take cosine, na? You'll get the real part. So it will be Vs magnitude into VR magnitude divided by B cos of beta minus delta minus A magnitude VR magnitude square divided by B magnitude into cos of beta minus alpha. Is it fine, guys? This way you can write the active power, and the reactive power you can replace cos with sine. You'll get the reactive power. I hope it is clear to everyone. Okay, so in terms of ABCD, you have calculated active and reactive. If you know the ABCD of short or medium or long, then you can put these values here. You can put the values of A, B and C, D and whatever, and VR and IR. You can easily calculate active power at the receiving end. And similarly, the receiving reactive power at the receiving end. So it will be Vs VR upon B magnitude sine of beta minus delta minus A magnitude VR magnitude square divided by B magnitude sine of beta minus alpha. Is it fine, guys? Tell me. This way you can calculate the reactive power. I hope it is clear to everyone. Tell me, guys, is it fine? So we have calculated active and we have calculated reactive in terms of ABCD parameter. Once you know the ABCD parameter of transmission line, you can easily calculate receiving end, active and reactive. Let's come to the short transmission line. In short transmission line, we know that A is 1 and B is Z, Z angle theta Z. So you can put the value of Z angle, B as Z angle theta Z, okay? So the beta will become theta Z, no? Beta will be angle of this Z. We call it theta Z. Is it fine? So this way you can put the values here and then you can calculate the active power. Let's take a case. If I say that the line is short, there is a short transmission line, and in the short transmission line, the line resistance is 0. If I take line resistance as 0, then Z will become 0 plus Jx. Is it fine, guys? So you can say that A will be 1 in the short transmission line and B will be equal to X angle 90. Is it fine? B will be equal to the magnitude of Z and angle is 90. So it will be 1 and B will be equal to X angle 90. And this is my VR, let's call it VR angle 0. And this will be my VS angle delta. Okay. Now what will be the active power at the receiving end? So active power at the receiving end, what you can do is, you can place A as 1, B as X, beta as 90 and alpha as 0. Alpha is the angle of A. Alpha is the angle of A. So angle came out to be 0 here. Okay, angle came out to be 0 here. So if I put the values, Vs into VR upon X, Vs magnitude into VR magnitude upon X, cos of, tell me guys, cos of beta is 90 minus delta. 90 minus delta minus, tell me, A into VR square upon B. A is 1 and VR square upon B. B is X. Cos of, tell me guys, cos of beta is 90 minus 0. Is it fine? So this will become 0 because cos 90 is 0. And this will become sine delta. Okay. So active power at the receiving end is Vs VR upon X. Vs VR upon X sine delta. So this is my active power received at the receiving end. Is it fine, guys? Is it fine? So we have calculated the active power received at the receiving end. Now the question is, you can see that how to maximize this receiving end power. You can maximize this receiving end power by minimizing the X value. Reactance, line reactance you have to minimize. Now tell me how to minimize the line reactance. Tell me guys, how to minimize the line reactance. Tell me guys, is there any idea how to minimize the line reactance? I told you the line reactance can be minimized by using the bundled conductor or the parallel transmission line. Okay, parallel circuit transmission line. Using the parallel circuit transmission line or using the bundled conductor, you can minimize this X line reactance. You can minimize this line reactance. Okay, and you can transmit more power. Okay, I hope you understood it. Similarly, you can calculate the reactive power at the receiving end. Okay, you can calculate the reactive power at the receiving end. How to calculate the reactive power at the receiving end? You put beta as 90 and here it is 90, it is 0. So sine 90 is 1. Here you have to write 90 minus delta. 90 minus delta is cos delta. Okay, so it will be Vs VR, Vs magnitude into VR magnitude upon X. It will be cos delta because sine 90 minus delta is cos delta minus A is 1. A is 1. A is 1, na? So what you can do is, you can put A as 1, VR square upon X. Sine of 90 minus alpha, that is cos alpha. Oh, no, not cos alpha. Wait a minute. It will be sine 90 minus 0. So sine 90 is 1. So I have to write 1 only. Is it fine, guys? So this way you can write the reactive power. Okay, this way you can write the reactive power and the active power expression. It's very easy. It's easy peasy. I hope you understood it. Now let's proceed, guys. So I told you about the ABCD parameter and the power flow. And this power flow concept is applicable on all transmission line. What you need to do is you need to calculate ABCD. Once you know the ABCD of the line, let's say short transmission line or medium or long transmission line, you can put the values of ABCD and you can calculate the active power at the receiving end and the reactive power at the receiving end. I hope it is clear to everyone. Now let's come to the medium transmission line. In medium transmission line, there are two models. Okay, one is nominal pi model and one is nominal T model. Okay, nominal T model. So there are two models, nominal pi and nominal T. Let me tell you guys, you can see that this is a symmetric model. I told you that every line has to be symmetric and reciprocal. So you can say that this line is symmetric and reciprocal. This model is also symmetric and reciprocal. You can't use this model. You can't use, why don't you use this model, Z and Y? Tell me guys, for the medium transmission line, why don't you use this model? Tell me guys, what's the problem? What's the problem with this model? Tell me. This is sending end, this is receiving end. Why don't you use this model? And in medium transmission line, we have to take the admittance also. I mean the capacitance part. Leakage, again, you can neglect the leakage part, but you have to take the capacitive reactance. Na? Okay, so you have to take the capacitive reactance. Why are you not using this model? This model can be the possible model for the medium transmission line. Na? Why are you going with this model and this model? Because you need to make the line to be symmetric and reciprocal. This model is not symmetric. This model is reciprocal, but it is not symmetric. That's why I avoid this model. Okay, I avoid this model. But let me tell you guys, no model is the exact model, because if you are calculating, if you do the calculation via this model, you'll get different answer at the receiving end. Let's say you have fixed the sending end voltage. If you have fixed the sending end voltage and if you are calculating the receiving end voltage via this model, you'll get different answer. Via this model, you'll get different answer. It means no model is accurate model. No model is accurate model. Just remember, there will be error everywhere. So you will not get the exact answer. Okay, you will not get the exact answer using these models, but they are approximate model, you can say, or we call them nominal model. Okay, there are two words, nominal and equivalent. Equivalent is something different. Okay, these are the nominal model. So we follow these models, and using these models you can calculate the ABCD parameter. ABCD parameter of this line and ABCD parameter of this line. Let's try to calculate the ABCD parameter of this line first. Okay, or this line, whatever, because you have to take one model at least, and you have to calculate the ABCD parameter of that. If you get the ABCD parameter now, then you calculate the receiving and active power, sending and active power, reactive power, receiving and reactive power, and the voltage regulation. You can easily calculate that. Okay, so let's try to calculate the ABCD parameter of this pi model. Okay, so I have this pi model. I have this pi model. This is Z. This is Y by 2 here, and Y by 2 here. Now, how to calculate ABCD parameter? Because it's not necessary that you remember these parameters. Don't try to cram anything. It's a maybe 30-second process. We know that this is sending end voltage, this is receiving end voltage. Fine. This current is IR and this current is IS. This is sending end current. Now, what I need to do is to calculate ABCD parameter. I need to write sending end voltage and sending end current in terms of receiving end voltage and receiving end current. Once you get this A and B, once you get this A and B, C and D you can easily calculate. Okay, so I am more interested in calculating A and B only. Okay, I don't want to calculate C and D. You can easily calculate that. Okay, how to calculate A and B? We have to write Vs in terms of VR and IR. Okay, so you can see that this is IR. Can you calculate this current? Can you calculate this current? Tell me guys, this current has to be VR into Y by 2. VR into Y by 2. Okay, this current is this. Now, what is this current? This current came out to be IR plus VR into Y by 2. VR into Y by 2. Is it fine? You can calculate this current. Okay, now you can apply the KVL. Now you can apply the KVL. Vs minus this drop. You'll get this VR. So VR will be equal to Vs minus this drop, Z into this current. This current is IR plus VR into Y by 2. Is it fine, guys? This way you can write. Now you can calculate Vs from here. So Vs will be equal to, what is the coefficient of VR? The coefficient of VR is 1 here plus, you can see that Yz by 2. The coefficient of VR is Yz by 2, and this is minus here. If you take it on the left side, it will become Yz by 2. Is it fine? Plus the coefficient of IR, ZIR. Is it fine? So we have calculated A and B. Okay, so A will be 1 plus YZ by 2. 1 plus YZ by 2, and B is Z. Now we know that the line is symmetric and reciprocal. Whatever this A is, A equal to D. Okay, A equal to D. So you will get D also. Now how to calculate this B? Tell me guys, how to calculate this C? How to calculate this C? We know that AD minus BC has to be 1. So you can calculate the value of C. Is it fine? Once you get this A, B, C, D, then you can calculate the no load receiving end voltage. VR no load. VR no load is Vs upon A. You know this A. If you know the sending end voltage, you divide it with A, you will get the VR no load. Receiving end no load voltage you can calculate, and then receiving end full load voltage you have to calculate again, and then take the difference, and then you can calculate the voltage regulation. If you know this A, B, C, D, if you know this especially A and B, you can calculate the active power at the receiving end and the reactive power at the receiving end. Okay, so I think it's easy. Now if you are using this model, obviously ABCD parameter will be a bit different. Okay, and you can use this model also, and you can calculate voltage regulation, and again you can calculate the receiving end active power and reactive power. I hope it is clear to everyone. Is it fine guys? Can I proceed? Tell me, say yes or no. Tell me guys, is it clear? Can I proceed? Say yes or no. Please like this session. Please like this session. There are so many students who are not like, who have not liked this session. So please like this session guys. I want to make at least half century of the likes. Okay, so it's 39 now. So please like this. Okay, okay, let's proceed. Let's proceed. Now I want to tell you about the long transmission line. This is the most important line, long transmission line. Okay, long transmission line. Let me discuss about the long transmission line. Now the long transmission line is many students feel difficulty in long transmission line. Why they are feeling difficulty? Because you can't lump the long transmission line. If you look at this medium transmission line or short transmission line, what you have done is the entire length of the line can be lumped in a simple circuit. Can be modeled in a simple circuit. You can see that this is the model of the entire medium transmission line. Let's say the line length is 250 kilometers. So for that 250 kilometers, you have designed a model. But in case of long transmission line, you can't make a model. You can't lump that line because the line length is very large. If the line length is very large, then the voltage and the current will be the function of space. There will be a space function. There will be a traveling wave. There will be a traveling wave. It means let's say you have the line like this. You have the long transmission line like this. Now the problem with this line is, let's say here you have the sending end, here you have the sending end, and here you have the receiving end. Here you have the receiving end, ZL. Now the problem is VR here and VS here. Okay, so the problem is, let's say this is x equal to 0 and x equal to L. The length is very large. If the length is very large, then voltage at this position and this position will be different. Okay, the voltage will not be same. If the voltage between these 2 points is not same, let's say voltage at this point and the voltage at this point, if they are not same, even if the load is removed, even if you remove the load, the line length is that much large that the voltage at this point and this point will not be same. If the voltage is not same, there will be a current flow even without the load. If there is no load, then also you will see a voltage difference between 2 points in long transmission line. This is the main problem, guys. Because of that, even in the open circuit line, you have a current flow. If you close the switch, you have a current flow. Okay, there will be a current flow. I mean, the generator keep supplying the current, even if the load is not there. It means you can say that the KVL and KCL are not applicable here. You can't apply. Even if the open circuit line, you have a current flow. There is a current flow. That's the problem. So, so how to tackle this problem? How to analyze this? To analyze this, what you need to do is, you need to do some regress analysis. Okay. You have to find the voltage as a function of X. Voltage as a function of X and T. You need to calculate that. So I'm not going to do the entire proof. Let me write the final result of this voltage. So voltage as a function of X. Let's say you want to calculate the voltage as a function of position. At different position, the voltage will look like this. V plus e to the power minus gamma X plus v minus e to the power gamma x. Okay. Now what is this gamma and what is this v plus and v minus? V plus and v minus are some constant, some complex constant. Okay. They are some complex variable or not variable, complex constant, let's say, or complex, complex variable. Let's write it complex variable. Okay. So they are some complex variable, or maybe we'll look at them. What are this v plus and v minus? What is this gamma? Gamma is called propagation constant. Propagation constant. Now what is this propagation constant? Propagation constant will be root of r plus j omega l into g plus j omega c. This will be my propagation constant, and it has some real part and it has some imaginary part. Is it fine, guys? So gamma came out to be this alpha plus j beta. This is my gamma. Alpha is called attenuation. Alpha is called attenuation constant. Attenuation constant. Okay. Why it is called attenuation constant, I'll tell you. And beta is called phase constant. Okay. Beta is called phase constant. So in long transmission line, the solution of the voltage will be like this. Similarly, you can say that the current will also be a function of space and time. So current will be, let me write the space function only. I'll introduce the time later. Okay. First, I'm introducing the space function. So it will be I plus e to the power minus gamma x plus I minus e to the power minus plus gamma x. Okay. This will be the current expression. So the current will be like this. It is a traveling wave. Why I'm calling this traveling wave? I'll tell you why. Okay. So I told you that this will be the expression. Now let's put the value of gamma. If you put the value of gamma here, you'll get Vx equal to V plus e to the power minus alpha plus j beta into x plus V minus e to the power alpha plus j beta into x. Is it fine, guys? Okay. This is the variation of voltage with respect to space. Now I have to introduce the time function also, because voltage is not only the function of space, it is also the function of time. So if you are writing the time function also, then it will be V plus e to the power minus of alpha plus j beta into x into e to the power j omega t. Okay. For the time function, you can put e to the power j omega t, multiply here with e to the power j omega t, and it will become V minus e to the power minus of plus of, here you have to take plus, alpha plus j beta into x into e to the power j omega t. Okay. So this will be my voltage expression. Now you have to take the real part of this. So if you take the real part of this, it will become V plus e to the power minus alpha x cos of omega t minus beta x. Okay. Similarly, if you write this function, then if you take the real part of this, it will become V minus e to the power alpha x cos of omega t plus beta x. This will be my real part of this function. Now you can see that this wave is a traveling wave. We call it forward traveling wave, and this is the backward traveling wave. Why I am calling this forward traveling wave and why I am calling this backward traveling wave? Why this is the traveling? Why I am calling that this is the traveling wave? Why I am calling that this is the traveling wave? How to check it? Why I am calling this traveling wave? Let me show you. We have V plus e to the power minus alpha x cos of omega t minus beta x. I want to plot this. So what you can do is, let's plot it with respect to x. Let's plot it at t equal to 0. I want to plot it at t equal to 0. Put t equal to 0 value here. If you put t equal to 0 in this, it will become V plus e to the power alpha minus alpha x cos of beta x. So we have to plot this function. How to plot this function? This function will look like, this is the envelope which is exponentially decaying, and this is e to the power minus x. It is decaying with x now. And within this envelope, you have to show cosine function, cos of beta x. So this will be the line, guys. This will be the wave. Now this is at t equal to 0. If you take t equal to t1, at t equal to t1, this function will become v plus e to the power minus alpha x cos of omega t1 minus beta x, or you can write v plus e to the power minus alpha x cos of beta x minus omega t1. We can call it theta. It means it's a delayed function now. Everything is same. Only thing is this cosine wave has delayed. So now you can plot the function like this. This maxima has delayed. This maxima has delayed by small quantity. Okay. So now the wave will go like this. So at t equal to t1, this maxima has traveled by some distance, and it is traveling in this direction, and the amplitude is decreasing. While traveling in this positive direction, the amplitude is decreasing because of this alpha. That's why I call this alpha as attenuation constant, because this alpha is responsible for decaying the amplitude. Okay, this alpha is responsible. That's why I call it attenuation constant. Okay, and you can see that it is traveling in this direction. That's why I call it forward traveling wave. This is my forward traveling wave. Is it fine? This is my forward traveling wave. Now the question is, let's say alpha is 0. If alpha is 0, then the magnitude will not decrease. If I take alpha 0, if alpha is 0, if there is no attenuation, then at t equal to 0, the wave is like this. There will be no attenuation. At t equal to t1, the wave will remain same. The maxima has traveled by some distance. Okay, the maxima has traveled by some distance. We call it lossless line. When this alpha be 0, tell me guys, when this alpha be 0, whenever the r is 0 and g is 0. Whenever r and g are 0, then you can see that there will be no real part, only imaginary part will be there. Okay, if r is 0, let me write, if r is 0 and g is 0, then gamma will be equal to root of j omega L into j omega C. Okay, take this j omega out, so it will become j omega root LC. Is it fine guys? So you can see that alpha is 0 and beta came out to be omega root LC. It means attenuation constant will be 0. They said there will be no attenuation if line is lossless. We call it lossless line. In lossless transmission line, there will be no attenuation. Okay, there will be no attenuation and the wave will travel like this. Now why I am calling it forward traveling wave? Because it is traveling in forward direction. The maxima is traveling in positive direction. That's why I am calling it forward traveling wave. Okay, now with what speed this wave is traveling? To calculate that, what you can do is you can put this internal term equal to constant, because let's say you are running with this wave. Let's say you are running with this wave with the same speed. Now, if you are running with this wave and whatever the wave speed is, you are running with the same speed. If you are running with the same speed as the wave is traveling, then you will see the same value of the function. Because at t equal to t1, let's say you are looking this value. At t equal to 0, you are looking this value. At t equal to t1, you are looking this value, because your speed and the wave speed is same. If your speed and the wave speed is same, then you will see a constant value of this function. The constant value of this function can only be happen if omega t minus beta x become constant. Okay, now you can take the derivative on both sides. So dxt by dt came out to be omega by beta. This is the velocity of the wave. Remember guys, omega by beta. Okay, this will be the velocity of the wave. With this velocity, the wave is traveling. Now beta, for lossless line, beta is omega root LC. So for lossless line, the velocity of the wave is omega divided by omega root LC. This L and omega is cancelled, 1 by root LC. Now it's a very interesting case. Now this is very interesting case. Okay, it means on lossless transmission line, L and C will decide the speed of the wave. Okay, this L and C will decide with which speed the wave is traveling, with which speed the voltage is traveling. Okay, so remember, this is very important. Okay, so I told you what is the speed of the wave. Now look at this wave. This is the backward traveling wave. Why I am calling this backward traveling wave? Because in this case at t equal to 0, it will be cos beta x. It is similar to this white color. Now at t equal to t1, it will become omega t1 plus beta x. It means it's advanced, beta x plus omega t1. It is not minus now. It is becoming plus here. It is becoming plus here. So it means the wave is not going backward. The wave is going on this side. The wave is moving on this side. That's why I call this as backward traveling wave. Or you can also calculate the velocity of this wave. If you take it constant and if you take the derivative, then dx by dt will be minus omega by beta. It will become minus omega by beta. What you can do is you can put this like this, na? Omega plus beta x is some constant, okay? And take the derivative on both sides. If you take the derivative on both sides with respect to time, dx by dt will be minus omega by beta. So the velocity will be negative here. It means this wave is traveling in backward direction, okay? So that's why I call it backward wave. I hope you understood. So on long transmission line, voltage will be a function of space and time. The voltage will be a function of space and time, okay? And the voltage will be of traveling nature, and the current will also be of traveling nature. Now, we can find the relation between voltage and current. On long transmission line, we can find the relation between voltage and current. How to find the relation between voltage and current? Let me tell you guys. We know that Vx equal to V plus e to the power minus gamma x plus V minus e to the power gamma x. Now, the current Ix will be equal to I plus e to the power minus gamma x plus I minus e to the power gamma x. Okay. Now, I am not going to prove it, but you can write this I plus as V plus by some ZC and I minus as V minus divided by minus ZC. Okay. Now, what is this ZC? ZC is called surge impedance. Surge impedance, okay. ZC is called surge impedance. Now, how to calculate this surge impedance or characteristic impedance? Surge impedance is R plus J omega L divided by G plus J omega C. This way you can calculate the surge impedance. For lossless line, the surge impedance will be, you can take R equal to 0 and G equal to 0. For lossless line, R is 0 and G is 0. So if you put R equal to 0 and G equal to 0, then the surge impedance will be equal to root of L by C. ZC will be equal to root of L by C. Is it fine, guys? It means it's a purely real quantity. Now, how to define the surge impedance? Surge impedance can be defined as the impedance seen by the forward traveling wave, because from here you can see that ZC is V plus over I plus. It means it is the voltage of the forward traveling wave and the current of the forward traveling wave. So you can say that the ZC is the impedance seen by the forward traveling wave. Or from here you can see that minus ZC is equal to V minus over I minus. It means the impedance seen by the backward traveling wave is minus ZC. The impedance seen by the backward traveling wave is minus ZC, and the impedance seen by the forward traveling wave is ZC. Okay. So this way you can comment on the characteristic impedance. What is the meaning of characteristic impedance? Impedance seen by the backward traveling wave is minus ZC. It means it has negative resistance. Impedance seen by the backward traveling wave is negative. Now, if the impedance seen by the backward traveling wave is negative, it means it is carrying the power back. Okay, it is carrying the power back. It is carrying backside. I mean, the power is reflected now. This backward traveling wave is taking the power back. Okay. So this wave, remember, this wave is dangerous because it is carrying the power back. It will carry the reflected power. Okay. I call it reflected wave also. Okay. It will take the power back. I hope you understood it. So I told you I plus and I minus, you can replace it with this. Okay. So if you replace it, then the expression Vx or maybe Ix will be equal to V plus by ZC e to the power minus gamma x minus V minus by ZC e to the power gamma x. Is it fine, guys? So you can replace this I minus with this and I plus with this. I hope you understood it. Now what you can do is you put x equal to 0. If you put x equal to 0 in this expression and in this expression, now what is voltage at x equal to 0? Voltage at x equal to 0 will be the sending end voltage. Okay. So if you put x equal to 0 in this expression, I'll say sending end voltage will be equal to, you put x equal to 0. So it will be V plus V minus. Is it fine? And in this expression, if you put x equal to 0, then it will become sending end current Is. Okay. So Is will be V plus by ZC minus V minus by ZC. Is it fine, guys? So we have calculated the relation between V plus and V minus. There are two equations now. From this, I can say that V plus minus V minus is equal to Is into ZC. Okay. So we have calculated V plus plus V minus like this and V plus minus V minus like this. So from these two relations, we can calculate V plus as well as V minus. Okay. Now what is V plus and what is V minus? I told you now, there are complex variable. Okay, so you can calculate the V plus and the V minus value. How to calculate? Just add these two values. So V plus will be equal to Vs plus Is into Zs by 2, and V minus came out to be Vs minus Is into Zs by 2. Okay, so this way you can calculate V plus and V minus from these two relations. Now what you can do is you can put these values here in this expression. V plus and V minus, you can put these values. Okay, once you put these values, then what will you get? Let me write. Okay, now what will you get? Let me write this. So Vx will be equal to, now you will get Vx equal to V plus. V plus is Vs plus Is into Zs divide by 2 into e to the power minus gamma x. Okay, plus Vs minus Is into Zs by 2 e to the power gamma x. Okay, so I have put the value of V plus and V minus in this expression. In this expression, I have put the value of V plus and V minus. Now you can simplify it. If you can simplify it, you'll get Vs, the coefficient of Vs is cos hyperbolic gamma x. Okay, plus the coefficient of Is and Zs will be equal to, sine hyperbolic gamma x. Okay, sine hyperbolic gamma x. Is it fine, guys? So we have calculated the coefficient of Vs and Is. Now what we can do is we can put the value of x equal to L. If you put x equal to L, then the Vx will become equal to Vr. So what you can say is, here you can say Vr is equal to Vs cos hyperbolic gamma L plus Is into Zs, and what will this become? Wait a minute, here it should be minus. Okay, here it should be minus. Now it will become, let me write this. Now Vs into cos hyperbolic gamma L minus Is into Zs sine hyperbolic gamma L. Is it fine? So you have written Vr in terms of Vs and Is. Similarly, from this equation, Is equation, from this equation, you can put value of V plus and V minus, and you can calculate IR also. So IR will be, let me write IR. IR will be minus Vs into sine hyperbolic. I don't know whether it is correct or not. Okay, but it should be like this. Sine hyperbolic gamma L Vs by Zs or Zc. Vs by Zc, not Zs. Zs is not there. Zc is there. Okay, it must be Zc. I am pretty sure that maximum of you have not studied this. Tell me, guys, how many of you have studied all these things? How many of you have studied all these things? Tell me, everyone. Have you studied all these things? Tell me, everyone. Now you can calculate IR, na? Now we can calculate IR minus Vs by Zc sine hyperbolic gamma L plus Is cos hyperbolic gamma L. Is it fine? So this way you can calculate VRIR and VSIS. Now you have calculated VRIR in terms of VSIS. So you can write them in matrix and you can get ABCD parameter of the line. Okay. Now you are getting VSIR in terms of VSIS. So what you can do is you can also calculate VSIS in terms of VRIR. So the expression will look like this. If you are getting VSIS in terms of VRIR, you will get the expression like this. Cos hyperbolic gamma L. Okay. Cos hyperbolic gamma L here, and here you have Zc sine hyperbolic gamma L, sine hyperbolic gamma 1 by Zc sine hyperbolic gamma L, and here you have cos hyperbolic gamma L. Is it fine, guys? This way you can write the ABCD parameter of long transmission line. Why these are important? Why these? I told you na, A is very important. A is very important. Why A is important? Tell me, guys. Why A is important? Because using A, you can calculate no load voltage at the receiving end. At the receiving end, you can calculate the no load voltage. And in long transmission line, no load voltage is higher than the sending end voltage. Why? Because generally it is less than 1. So at the receiving end, if I calculate the no load voltage, that no load voltage will be sending end voltage divided by A. A is this cos hyperbolic gamma L. If you put the cos hyperbolic gamma L value, if you put the cos, this is less than 1. This came out to be less than 1. If it is less than 1, no load voltage will be greater than the sending end voltage. Okay. It's called Ferranti effect. Is it fine, guys? Is it fine, guys? Tell me, have you understood it? So I know that maximum students have not studied this. I don't know why you have not studied this, because this is very important. In previous year question, in previous year, you'll find these questions. The no load voltage. Okay. They ask you about the no load voltage at the receiving end of the long transmission line. Okay. This question came out, I mean, 2 or 3 times. I don't know how many times this was asked. At least 3 times they have asked it. Okay. So you have to be careful, guys. Now, if the line is lossless, that's a line is lossless, then gamma is equal to J beta. For lossless line, gamma will be equal to J beta. If gamma came out to be equal to J beta, then this cos hyperbolic J beta L will become cos beta L. This will become cos beta L, and this will become JZC sin beta L. Okay, and this will become J by ZC sin beta L, and this will become cos beta L. Now hyperbolic function will not be there for lossless line. Okay, into VRIR, and on this side you have VSIS. Is it fine, guys? VSIS. Is it fine? So this way you can calculate ABCD parameter of the line. Have you understood it? Okay, have you understood it? So I have calculated the ABCD parameter of the long transmission line. I told you how I have calculated this. First I have calculated V plus and V minus, then I put the value of V plus and V minus in this expression, and then I simplified it. Okay, so this way you can calculate ABCD parameter. Now ABCD parameter are very important. Why? Because you have to calculate the active power at the receiving end and the reactive power at the receiving end and the voltage regulation at the receiving end. I hope it is clear to everyone. Now what I can do is, using this ABCD parameter, what we can have is, we can make equivalent pi and equivalent T model of the long transmission line. Again, it is asked in the previous year questions. Equivalent pi and equivalent T model of the transmission line. How you are going to make it? How you are going to make the equivalent pi and equivalent T model of the transmission line? Now, the pi model and T model of this long transmission line cannot exist. Why? Because you can't lump it. There is no lumping of the long transmission line. It is not correct. You can't make nominal pi and nominal T because they don't exist. But you can make equivalent pi and equivalent T. Now look, I'm using 2 words. One is equivalent, one is nominal. Equivalent means it is not actually existing. Equivalent means it's not actually existing. Okay, and nominal means, I mean, you can use these parameter. I mean, you can lump the medium transmission line like this. Okay, so that's why the nominal word is used. But in equivalent, what we are using is, in equivalent you will get the exact answer which you are getting from this. You will get the exact answer if you are using the equivalent pi model, because you are using these parameter to draw the pi model or T model, but it will not exist for long transmission. Let me tell you guys, that's why I am using equivalent model. It's not actually exist. Okay, so let me draw the pi model of this long transmission line. If you want to draw the pi model of the long transmission line, tell me how to draw the pi model of the long transmission line, equivalent pi model of the long transmission line. How you will draw the equivalent pi model? Equivalent pi model of the line. Tell me how you are going to draw it. If you want to draw the equivalent pi model, then what you can say, this is Z, this is Y by 2, and this is Y by 2. Now we need to calculate this Z value. We know that if this is the pi model, then A must be equal to 1 plus YZ by 2, and B must be Z. We have already calculated A and B for long transmission line. Okay, so what you can do is, you can put Z equal to JZC sin beta L. Okay, this is my Z, and using this Z we can also calculate this one. A must be equal to, what is A? Cos beta L. Okay, so you can calculate Y by 2 also. So in place of y by 2, you put the value you calculate from here, and in place of z, you can put this value. This is my equivalent pi model. Okay, using the ABCD parameter, you can draw the equivalent pi model of the long transmission line. But let me tell you guys, for long transmission line, pi model and T model will not exist because you can't lump the line. Lumping will not be there for the long transmission line. Okay, remember this point. Okay, I told you about the lossless transmission line, and in lossless transmission line, alpha is 0, beta is this. Now, what is the meaning of beta? Beta, I told you, beta is the phase constant. Beta is phase constant. What is the meaning of phase constant? Phase constant will say that how much phase change per unit length. If the line is traveling unit length, let's say the line is traveling unit length, then how much phase has changed? Obviously, there is a phase shift. Nah, that's why it's going in this direction, because there is a phase shift. Phase is shifting, na? Beta x minus theta. So it is shifting. Now, how much phase is shift per unit length? If you have traveled unit length, then how much phase is changed? We know that in lambda wavelength, in lambda length, if you are traveling lambda length, the phase change is always 2 pi. So if you are going unit length, then the phase change will be 2 pi by lambda. So this is the phase change per unit length. This is the phase change per unit. So beta has to be 2 pi by lambda. Is it fine? So beta came out to be 2 pi by lambda, and beta for lossless line is omega root LC also. So you can write like this. And the surge impedance is this. Okay. And these are the sending end voltage and sending end current in terms of receiving end voltage and receiving end current for lossless transmission line. I hope it is clear to everyone. Tell me guys, is it clear or not? I hope this is clear. Now, I want to tell you one more point. Because that is again important. That will help you in defining the surge impedance loading. Okay, SIL. Now, what is the meaning of SIL? Let me tell you. Let's say you have a lossless transmission line. Long transmission line, and it is lossless. You have a lossless transmission line. Lossless transmission line. You have a lossless transmission line. In lossless transmission line, the surge impedance is root L by C. We know that. Okay, and if I connect ZL here, and if you want to look at the input impedance at any location, let's say at this location, you want to calculate how much impedance will look. You will see from this point how much impedance you will see. Let's say you want to calculate the input impedance of the line. From some point, let's say from some point you want to look at the input impedance. And how to calculate that input impedance? It's very simple, guys. What you can do is, let's say this length is L equal to 0, and let's say this length is L equal to L, let's say. From this length L, now we are looking from the load side. At some length L from the load, at some length L from the load side, from the load terminal, at some length L, if you want to look at the input impedance, then the input impedance formula will be, at some length L, the input impedance formula will be ZC. You have to remember it. If you don't know the process, if you don't know the derivation, so I don't want to do the derivation right now, because there are so many students who get lost in the derivation, so they stop watching the video. So what you can do is, you can remember this formula. So the impedance seen at any length L, is equal to ZC into ZL cos hyperbolic gamma L plus ZL cos hyperbolic gamma L, because you are looking at the L distance, na? So ZL cos hyperbolic gamma L, ZC sin hyperbolic gamma L, okay, gamma L, divided by ZC cos hyperbolic gamma L plus ZL sin hyperbolic gamma L. I hope it is clear to everyone. This is the input impedance. This is the input impedance seen by the line at some L length. If the line is lossless, then gamma can be replaced with J beta. So the input impedance at length L will be equal to ZC. You replace gamma with J beta, so it will become ZL cos beta L. You have to remember these formulas, guys. Plus JZC sin beta L. Sin beta L divided by ZC, this should be ZL. This is ZC cos beta L plus JZL sin beta L. Okay, is it fine, guys? So this way you can write input impedance. Now, if the line is lossless and it is short circuited, let's say, if the line is lossless and I have shorted it, Now if you have sorted it, you can put the value of ZL equal to 0. If you put ZL equal to 0, then short circuit input impedance, if you are looking at any length, the input impedance at any length L, okay, so the ZL will look like this. ZL will be equal to, this L will be 0, this will be 0, so it will become, ZC will cancel, so it will become JZC 10 beta L. Is it fine, guys? This will be my ZL short circuit. If the line is short circuited, and if you are looking at any length L, if you are looking at the input impedance, then this will be the input impedance. Now ZL open circuit. What is ZL open circuit? If the line is open circuit, let's say, if the line is open circuit, then if the line is open circuit, okay, here it is open circuited, and you are looking input impedance ZL. You are looking the input impedance ZL. What will be the input impedance? You can put ZL as infinite. Okay, so better you take common this ZL and calculate this value. This value came out to be minus J, wait a minute, ZL open circuit will be equal to, if you want to calculate ZL open circuit, it will be equal to minus J ZC cot beta L. Okay, this will be by Z open circuit. You can put ZL equal to infinite. Take this ZL common and then you can calculate this value. Okay, I hope it is clear to everyone. Now what you can see is, if you multiply this ZL open circuit and ZL short circuit, then ZL open circuit of lossless line into ZL open short circuit, then this product will be equal to tan beta L and cot beta L will cancel. It will become ZC square. So from here you can calculate surge impedance. Surge impedance is geometric mean of surge impedance is the geometric mean of impedance seen for the open circuit, impedance seen at the open circuit transfer line and the impedance seen of short circuit transfer line. So you can calculate the surge impedance of the line. So this is the other definition of surge impedance. Okay, this is the next definition of the surge impedance. Surge impedance is the geometric mean of this. Okay, now what you can do is, now let's try, let's give it one more try. So I told you how to calculate the ZC. There is one more term, we call it reflection coefficient. Reflection coefficient is ZL minus, reflection coefficient at the load end. Reflection coefficient at the load end is ZL minus ZC divided by ZL plus ZC. This is the reflection coefficient. Now what is the meaning of reflection coefficient? Reflection coefficient at the load is reflected wave upon incident wave. Reflected wave upon incident wave. Incident wave. This is my reflection coefficient. Now you have to remember it. If you don't know the derivation, no worries, you have to remember this formula. This is the reflection coefficient, guys. Now if I terminate the line, let's say the lossless line is there, and if I terminate the line with its surge impedance, the load impedance is equal to surge impedance, ZC. Okay, now what will be the reflection coefficient, guys? Tell me. The reflection coefficient at the load end is 0. The reflection coefficient at the load end is 0. What does it mean? It means reflected wave will be 0. There will be no reflected wave. If the line is terminated with the characteristic impedance or the surge impedance, then there will be no reflection on the line. It means there will be only forward traveling wave. There will be only forward traveling wave. Is it fine, guys? So what you can say is, you can define the surge impedance now. The surge impedance is the impedance of the line by which, the surge impedance is that impedance by which if the line is terminated, then there will be no reflection. Okay, let me repeat this. Now these are the definition of the surge impedance. Now there are so many definitions of the surge impedance. So surge impedance is the impedance by which if line is terminated, then there will be no reflection. We call that impedance as the surge impedance, or you can say maximum power is going to be transferred here. Okay, we call it maximum power is transferred here. Okay, we call it surge impedance. So there are so many definitions of surge impedance. One definition is this: if the line is terminated with the impedance such that there is no reflection, we call that impedance as surge impedance. This is the one definition. And there is one more definition. Surge impedance is the geometric mean of ZL open circuit and ZL short circuit. There is one more definition of surge impedance. The definition of the surge impedance is it is the impedance seen by the forward traveling wave. It is the impedance seen by the forward traveling wave. So there are so many definitions of surge impedance. Okay, you have to be careful because they can ask you MSQ, multiple select question on that. Okay, so I told you what is the meaning of surge impedance. Now what is surge impedance loading? Let's say I have a line, I have a lossless line, and I terminate this line with surge impedance. Now can you calculate the power transfer to this? Since this is the single phase model, so let's say the line voltage is VL. So what you do is you divide it with √3. Okay, this is the phase voltage, and let's say this is the voltage across this receiving end. This is the voltage across this load. So you take the square of this, divide by the surge impedance. This is the power delivered to this, because the surge impedance is √L/C, because I am taking lossless line. This surge impedance is purely real. Okay, so now how much power is transferred here? If I terminate the line with the surge impedance, tell me how much power is transferred to the impedance. What you can do is you can calculate the load terminal voltage. So load terminal voltage came out to be VL, let's say, and this is the line voltage. So the phase voltage will be VL by √3. You take the phase voltage square, divide by ZC. This is the power transferred to this ZC per phase. But in 3 phase, you have to multiply it with 3. We call it surge impedance loading. We call it surge impedance loading. Is it fine, guys? Now the meaning of surge impedance loading is, for a lossless line, if you terminate the line with the surge impedance, then how much power is transferred to that surge impedance? We call that power as surge impedance loading. Okay, so you can calculate, it will be equal to VL square divided by ZC, and you can put the value of ZC. Okay, so this way you can calculate surge impedance loading. I hope it is clear to everyone. So I told you about the long transmission line, how the parameter will look like, and how to calculate these parameter, what is the meaning of alpha and beta, and how to calculate this alpha and beta, what is the meaning of lossless transmission line, what is the meaning of surge impedance. Okay, so, and how you are calculating the input impedance from at any length L, let's say. Okay, from any length L, you can calculate this impedance. Okay, so this way you can calculate all these parameters, guys. So here I can stop the long transmission analysis. Now there is one more topic we call reflection on transmission line, and or you can say transient on transmission line, and there is one more topic, compensation, and there is per unit. I have to take these chapters also, but since the time is over, I have to take this class only for 2 hours. From now on, Ashutosh sir will carry on. So but I have one more class now. I have to take one more class. In the next class, I will teach you about the per unit. I'll start from the per unit analysis, and then I'll go for load power flow. Okay, load flow studies. Okay, I'll tell you about the load flow studies, and then I will go with the symmetrical fault. Okay, so that topic I'll cover in the next class. So because the topic is not covered, only the transmission line part is covered. So anyway, don't worry, guys. I'll cover the remaining part also. So I hope you enjoyed it. But let me talk to Ashutosh sir, and then he will take some questions. Okay, I'll take some questions, because I thought that the maximum students are lagging in the concepts, because if you don't know the concept, then how can you solve the questions? The problem is, let's say I take some question and you don't know the concept, and I am applying the formula, so you are cramming the formula, you will cram the formula. That's why I am revising the concept. No doubt solving problems is again a good idea. You can solve PYQs, or you can solve some problem, so that you get the experience of, I mean, you can revise all the formulas. But that's why, I mean, I don't want to revise the concept, like I don't want to revise, or I don't want to revise the formulas. Okay, I don't want to solve the questions with the help of formulas. That's why I am telling you the concept. Okay, if you remember these formula, you can easily solve the questions also. Okay, so anyway, don't worry, we'll take the question also, and you'll enjoy those questions anyway. Okay, so don't worry about that, we'll take the questions also, and in the next class I'll take some questions. Okay, so let's stop it here, and let me talk to Ashutosh sir, and then he will carry on. Wait a minute, guys. So there will be a glitch of 10-15 seconds, and then he will join. But before that, let me talk to him, and sir will continue from this point. So wait a minute, guys. So guys, sir will continue within maybe 2-3 minutes, and he will join you just after 2-3 minutes. So let's talk maybe, because we have only 2-3 minutes, so better we talk about your preparation. How's your preparation going? Tell me, guys. How's your preparation going? Have you studied these concepts before? Tell me. Say yes or no. Have you studied all these concepts? Say yes or no. Have you studied all these concepts? Tell me, everyone. Have you studied all these concepts like input impedance, reflection coefficient, and then this open circuit line impedance, short circuit line impedance? Okay. And okay, sir has already okay, sir. Sir has told that he's ready. So let me stop and sir will continue from this point onward. Okay. So thank you, guys, and see you tomorrow. On tomorrow we'll take the other topics also. Okay. So thank you.
Hello friends, I welcome you on BYJU'S Exam Prep, India's most comprehensive preparation platform for all the engineers, all the candidates who are live with me. Just quickly confirm your presence in the comment section and tell me whether my audio visual quality, everything is clear. Yes, everybody, a very warm welcome to all of you. A very good evening to all of you. I hope you are enjoying Ashu Jhangra sir. And now I will carry forward some of the topics. So everybody just once confirm about the audio and visual quality. Everything is clear? Yes, everyone. So before I start the session, let me just brief you that what are the topics I'm going to cover in this particular session, because me and Ashu Jhangra sir, we both are taking this particular subject, power system. So we have divided the subject between us. Some of the topics I'm taking, some of the topics sir is taking. So today, what are the topics I'm going to discuss, that I will tell you. But before that, some of you may be joining me for the first time, so there is a brief introduction about myself. My name is Ashutosh, as you can see on the screen, 11 plus years of teaching experience. MTech from IIT BHU in 2010, some of the books I have written, and these are my areas of expertise. Before we start the session, everybody just hit the like button, hit the bell icon so that you get all the notifications in time, and do not forget to subscribe to BYJU'S Exam Prep so that you do not miss any of the important session, your favorite session. You must be aware that right now we are running the Maha Marathon series, which is a GATE 2023 booster series, daily 10 a.m. in the morning, and 4 p.m. also some sessions are planned. And your favorite faculties for electrical, electronics, instrumentation, and computer science. 15th of January, everybody's favorite, my favorite, Abhinav Negi sir is going to take a mega workshop on 7 success mantras for a beginner, from a beginner to a topper in GATE 2024. It is going to be conducted on 12:30 p.m. on 15th of January. So if you have any juniors, if you have any colleagues, share this session to them. It is actually a workshop. So if you want to attend this workshop, you have to get yourself registered. I will tell you, Gram, what are the topics I'm going to cover. Just wait a while. And once again, our favorite Rakesh sir is going to bring one of the most awaited session for the year, that is 15 marks in just 15 hours. So stay connected. 2 legendary faculties for mathematics, Rakesh sir and Ankit Joshi sir, they are going to make impossible as I am possible. And this session, within just 2 days, the complete mathematics is going to be completed by Rakesh sir and Ankit sir. So stay connected. Once again, today, that is 8th of January, 12 p.m. in the afternoon, there was a scholarship test where you can get up to 90% scholarship. And we have the best in class GATE and engineering services test series, where you can attend full length mock tests, subject tests. Some of the important features are you will be getting 60 plus tests covering GATE and EAC, detailed mock analysis, virtual scientific calculator, 4,000 plus practice questions, all India open mocks. And more than that, all these test series are being curated by the GATE experts. So let me just tell you what are the topics I'm going to cover. The first topic that I'm going to cover, let me use another color, is overhead line insulator. Overhead line insulator. The second topic that I will be covering is insulated cables. or we also call it as underground cable. The third topic that I am going to take today is HVDC transmission. And the fourth topic that I will be covering is power distribution. So these four topics I will be covering today. Then in the second part of the session for power system, I will be covering the remaining portion which is assigned to me. So once again, guys, before we start, let us take 2 minutes so that I can come to your level and you can come to my level. So just tell me how you enjoyed Ashu Jangra sir class. I was watching a little bit of it and I think you got some really important inputs from Ashu sir. So you enjoyed the class? Yes, everybody? Yes, a very good evening to all of you. See, one thing I want to add here, see, it is not restricted that we are only going to talk in English. So, koi bhi bacha aisa hai, if anybody is there, that if you have any problem regarding English, you can ask me then and there. I can use English also, Hindi also, and if you force me, I can use Bhojpuri also. But Bhojpuri, I am just joking. I am not going to use Bhojpuri, otherwise it will be very difficult for you to understand. So friends, let us start without wasting much time. I hope you enjoyed the session. But before I start, I will request everybody just quickly hit the like button and share the session with your friends and colleagues so that more and more people are going to be joining with us. Now, before I start, let me just tell you that how I'm going to approach this particular session, because it is a revision session. I'm going to give you almost approximately a complete revision. For that, you just sit back, relax, and understand the story. In the form of a story, I'm going to tell you the revision part. And I will also tell you some of the problems also, because unless you solve the problems, you will not get the confidence that's how you are dealing with the concept. So everybody, let us start with the overhead line insulator. Overhead line insulator. Before we start overhead line insulator, I want to ask you, why do we require insulator? What is the purpose of insulator? Please understand. What is the purpose of insulator? Let me add one page here. Let me add one page here. Okay. We are talking about overhead line insulator. Now this is your transmission tower, which we call as pylon. In some of the countries, especially European countries and American countries, they are calling it pylon. This is your transmission tower. And this is, suppose, a string type, suspension type string insulator. And this is your live conductor. This is your live conductor. So why we require the insulation? We require the insulation. Or insulator to minimize leakage current. Yes or no? सबसे बड़ी समस्या क्या है? लीकेज करंट. कितना भी अच्छा, कितना भी ideal, how much ideal insulator you are going to use, still there will be some leakage current flowing from this conductor, this live conductor, to the ground with this path. So the agenda of using insulator is that how you can minimize this leakage current. This is the first thing. So when we are talking about insulator, we want to protect our transmission line. We want to protect line against what? Operating voltage. Against operating voltage. Yes or no? Tell me yes or no in the comment section. Why we require insulator? Because we want to reduce the leakage current. We cannot remove it. How much ideal insulator you are going to use, you cannot say that 100% leakage current is reduced. Some leakage current will always be there. And by using insulator, we are protecting our system, protecting our line against the operating voltage. There is one more term which is very much similar, that is insulation level. What is this insulation level? Insulation level is basically used to define the maximum over voltages may be present in the system, and the two possibilities are lightning over voltage and switching over voltage. What is lightning over voltage? I want to give you some idea, because previous year there was a question asked on this. Okay, so let me give you some idea about the lightning over voltage. Suppose this is your transmission tower. There is one more transmission tower. And suppose this is your transmission line. Suppose because of some reason the lightning is going to strike here. Lightning will strike in the form of a huge amount of static charge being discharged on the transmission line. Yes or no? The moment this lightning stroke is going to strike the transmission line, this discharge current will be divided into two parts. Now you will ask me, sir, why two parts? Because the impedance seen by this discharge current is going to be the surge impedance. Now surge impedance is independent of the length of the line. Surge impedance is independent of the length of the line because it is the ratio of inductance and capacitance. So whatever be the point at which the lightning is going to strike, always the discharge current will see both the sides impedance as same. So the discharge current will be approximately divided into two equal parts, and these transmission towers are going to be grounded. Now there is a very classical question being asked, what can be, suppose if this is a point P, what can be the over voltage at point P? So it is going to be 1 by 2 IC into ZC. You can expect one question on this. Is it clear, everybody? Just tell me yes or no in the comment section. Are you able to follow this? So this is the difference between how we define the insulation level. Insulation level, we are protecting our system against the over voltages, possible over voltages. For example, lightning over voltage and switching over voltages. If you want to design your transmission line, the design criteria in terms of insulation level, if the voltage is less than approximately 300 kilovolt, then it is going to be lightning over voltage. But if the voltage is more than 300 kilovolts, some books are writing 220 kilovolts also, but 300 kilovolts is approximately that you can take as switching over voltage. Now what happens? Very easily you can say that lightning over voltage is going to be more dangerous in comparison to the switching over voltage, but the problem with switching over voltage is this is an internal phenomena. Which deals with the transients, and it is very difficult to control, it is very difficult to protect. Whereas for lightning over voltage, you can use the ground wire, you can use the surge arrestor like that. Ground wire is nothing but a wire which is connected at the top of the transmission tower. And what is the purpose of it? The purpose of it is, instead of this lightning striking the conductor, it is going to strike the ground wire. And this is the reason that above a certain voltage, more than 300 kilovolts, the switching over voltage is being the criteria for deciding the insulation level of your transmission system. Is it clear, everybody? So this was about the insulation level, but right now we are talking about insulator, that is overhead line insulator. Okay, overhead line insulator. Now the first and the most simplest type of overhead line insulator is the pin type insulator. It is used for voltages less than or equal to 33 kilovolts, not more than that. Now its structure, you can see there are a number of shells. These shells are called as petticoat shells because they are shaped like this. So they are called as petticoat shells. Now their shape is like that because if there is going to be anything deposited on its surface, then its dielectric strength is going to be reduced, and that is the reason the surface is smooth and it is like that, so that nothing deposit on its surface. There is a top shell, then there is a next shell, and there is a bottom shell, and their size is being reduced in a conical form so that nothing deposited and the dielectric strength is not marginalized. Now you see this pin type insulator, as the name indicates, the top side, the conductor groove is there. This is the conductor groove where conductor is placed, and at the bottom side there is a metal pin. Now this metal pin is directly connected to the cross arm of the transmission tower, and it is insulated by using this cement. But whenever there are two metal parts, two metal bodies, always there will be some leakage current present between them, and this conductor, this is the conductor conducting part, and this is cross arm or the metal pin which is also conducting, so there will be a leakage current path. This is called the leakage current path. There is an important concept on which question can be asked, that is the flashover distance. It is the minimum distance between the live conductor and the metal pin of the insulator, where there is a possibility of a direct flash over if the electric field strength is going to be extremely high. Is it clear? But there is a limitation on this pin type insulator, that it cannot be used for more than 33 kilovolts. The reason is, listen in the form of a story. You have all the notes. It's just a quick revision. Why it cannot be used for more than 33 kilovolts? Because if you have to use it for more than 33 kilovolts, the size and the number of these petticoat shells has to be increased, which becomes mechanically unstable and it is not economical. I hope you got it. Then we have shackle type insulator. Shackle type insulator is basically used whenever there is a dead end. Okay, dead end, or you can say railroad crossing, or basically you can say any geographical region which is not easy for establishing the transmission tower. So definitely it is important to maintain the tensile strength in the conductor so that the sag is minimum. So what we are doing in case of shackle type insulator, we are using two different towers for the conductors. This is one conductor, this is another conductor, two different towers, and this is shackle type insulator, and these two sections are connected by using a jumper. It is again a conductor, but this is used only for voltages less than 11 kilovolts. For voltages more than 11 kilovolts, we are using the horizontal string insulator. Okay, that is called a strain type insulator. We will discuss that also. Then we have stay wire insulator. Stay wire insulator, you can remember one of the famous Rajpal Yadav movie. I don't remember the name of that movie. You remember? he was coming from some village, coming to the city to take revenge, and he got his shoes dirty with the cow dung. So he was trying to clean it with the wire connected to the pole like this. You remember nearby your residence? So people thought he is electrocuted. So people started hitting him with the stick. So that was a funny moment in the movie. But you must have seen nearby your home or somewhere that there is a pole and there is a wire connected with the pole, and there is a, you can say, dark brown color insulator, which is egg type. This is called stay wire. This wire is a stay wire. Actually, it should not contain any current, but some leakage current is present. The very purpose of having this stay wire is to give the mechanical strength to the pole. These are the lines connected to the pole, and this is the stay wire. And to avoid the leakage current in the stay wire, we are using the stay wire insulator. Is it clear, everybody? Then we have the most practical overhead line insulator, that is the string insulator. Any individual disc in the string type insulator is going to look something like this. So this is the metal cap. This is the metal cap in which the other, you can say, insulator disc is going to be connected. And this is the metal pin below which another insulator disc is going to be connected. So this is how it is a string of insulator disc which is going to handle certain amount of voltage. Now this path is not uniform. It is curved. Why it is curved? It is curved because we want to increase the leakage path distance, leakage current distance, path distance, so that the leakage current is going to be minimum and there is less possibility of any direct flashover. I hope it is clear. Then we have a strain type string insulator. A strain type insulator is again used in the difficult geographical terrains where it is important to maintain the tensile strength in the conductor, and it is used for voltages more than 11 kilovolts. It is a string of insulator which is horizontal, which is parallel to the conductor itself. Now we have one of the most practically used overhead line insulator, that is suspension type string insulator. From its name itself you can understand it is going to suspend. It is going to suspend like this, and it is going to have number of insulator discs like this. Now some of the important features you can read from here. The beauty of this suspension type string insulator is that it is one of the most famous question being asked in various interviews, that can you tell me what is the operating voltage of this transmission line just by observing the line? So answer is yes. By counting the number of individual discs, you can tell if n is the number of insulator disc multiplied by 11 kilovolts line RMS voltage. Approximately this is going to be the operating voltage of the line. Every individual disc in this suspension type string insulator is going to handle approximately 11 kilovolt of the line RMS voltage. Now because of its free fall, it can swing because of the air pressure, and that is the reason the possibility of insulator string to be broken by the air pressure is minimum, because it is free to swing. It is free to swing. Now we are going to talk about the voltage distribution across the string type insulator. So we are going to model it. We are basically going to model this suspension type string insulator by using some electrical network components. Yes or no? Now basically there are two capacitances coming out. One capacitance is C dash. C dash is the capacitance, which is the capacitance I'm going to write here. C dash is the capacitance, which is the capacitance between the metal pin and tower or earth. So this is the metal pin, but it is directly connected to tower, so no capacitance is going to come here. This is the metal pin and this is a tower connected to earth, so there will be one capacitance C dash coming here. This is the metal pin and this is the tower, one more C dash, metal pin and the tower, one more. So you see, if there are total 4 insulator discs, the number of C dash capacitances you are getting is n minus 1, that is 3. We'll get one more capacitance, that is C. Now this is the mutual capacitance. See, we talk about mutual inductance, but the concept is different. We are simply using the name mutual here, but there is nothing mutual. Basically, we are talking about the individual capacitance of these insulated discs, because this is a metal part, this is a metal part, in between there is a dielectric, so there will be some capacitance that we are calling as C. Is it clear, everybody? Is it clear, everybody? Are you getting that? So if there are n insulated discs, how many number of C capacitance you are getting? 4. N, so it is N. C dash n minus 1. One important part I want to discuss here, that is important, you may get a question on this. Okay. So see here, if we talk about the capacitance C, generally we write it as epsilon A by D. Yes or no? So capacitance C is directly proportional to A. What is this A? This is the area of the insulator disc. Area of the insulator disc when we talk about C. When we talk about C dash, we write it as 1 upon length of the cross arm. Length of the cross arm. Why? You see that capacitance is directly proportional to the cross-sectional area, and when you talk about the capacitance C, the dominating part is the area of this insulated disc. The dominating part is, we'll talk about string efficiency, don't worry Ashu. Okay, let me go step by step, I cannot jump like this. You please have a little bit of patience. I will come to the string efficiency also. Okay, so what I was discussing, yes. So when you talk about this mutual capacitance C, it is dominated by that area of the insulated disc. It is dominated by the area of insulated disc. So I am writing C is directly proportional to A. This D is the distance between the two metal parts. So this is one metal part and this tower is the next metal part. So this is the length of the cross arm. This is the length of the cross arm. So when we are writing C dash, the dominating part is the length of the cross arm. So I am writing C dash as being inversely proportional to the length of the cross arm. Now you tell me, area of the insulated disc is going to be a high value or not? So this is a high value, so C is a high value. Length of the cross arm is high or low? It is more or less. Normally length of the cross arm is going to be around 6 to 8 meters. 6 to 8 meters in general I am saying. So this is going to be a high value. So because it is inversely proportional, so C dash is going to be a less value. So we are defining one more parameter here, that is K, as a ratio of C dash upon C, and it is always less than 1 because C dash is less than C. Hello, are you able to follow this? Are you able to follow this? Just tell me yes or no. Is it clear, everybody? Now, by using this parameter K, if you want to write the voltage distribution across various insulated discs, that is V1, V2, V3, V4. Let me give you some more input here because that would be better for your understanding purpose. Just give me 2 minutes. Suppose we are writing we are drawing the equivalent electrical network or model for this suspension type string insulator, and it is something like this. Suppose there are 4 units. Suppose there are 4 units. This is the conductor. Now please understand, we are defining the capacitances like C dash, C dash, C dash, C, 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 C. Now suppose the leakage current here is I4, here it is I3, here it is I2, and here it is I1. Now there is some current going in this path, that is I1 dash, here it is I2 dash, here it is I3 dash. Now these currents I1 dash, I2 dash and I3 dash are like charging currents. You remember charging current? Charging current, you remember in case of the transmission line, that charging current is a current which is sent from the sending end but does not reach to the receiving end. You see here, sent from the sending end but does not reach to the receiving end. Somewhere in between it is lost. Somewhere in between it is lost. Now, if these charging currents are not present, if the capacitances are same, my dear friend, then their capacitive reactance is also going to be same, and if the capacitive reactance is same, then the voltage drop across each insulator unit is going to be same, but that is not the case because I1 dash, I2 dash, I3 dash are present. So because of this I1 dash, I2 dash and I3 dash, the voltage across different units is different. Suppose it is V1 across the first unit, V2 across the second unit, V3 across the third unit, and V4 across the fourth unit. Now this V1, V2, V3, V4 you can write by using these equations. You can write V2, V3 and V4 in terms of V1. So V2 is V1 1 plus K. You can remember this because we cannot go for the derivation right now. We don't have that much bandwidth of time. You can understand. Okay. V3 is going to be V1 1 plus 3K plus K square. V4 is going to be, it's not V3, it is V1. It is V1 1 plus 6K 5K square plus K3. So you remember these 3 equations. Directly you can apply if you are getting a question on this in the examination. I'm giving it 7 stars. 7 stars. Okay. Twinkle, twinkle, little star. I hope it is clear. Okay. Now let me ask you a basic question. You are saying, sir, listen very carefully. You are saying, sir, you are saying V2 is V1 1 plus K. Okay, sir. What is V3? It is V1 1 plus 3K plus K square. Sir, what is V4? It is V1 1 plus 6K plus 5K square plus K cube. Now, sir, K is less than 1, but it is a positive value. It is a positive value. If it is a positive value, it means 100% confidently you can say that V4 is greater than V3, is greater than V2, is greater than V1. It means the maximum voltage stress which is handled by any insulator is going to be the insulator which is nearest to the line conductor, It means the total voltage which has to be handled by this string insulator, the majority of that voltage is being handled by the insulator near the conductor. It means the amount of insulator we are using here is going to be a waste. And whenever as an engineer we see there is something going waste, we talk about efficiency. So let us talk about string efficiency. String efficiency, what it tells you, it simply gives you what it tells you. First I am telling, then I will talk about the formula. It gives you the non-uniform voltage distribution across the string, across the insulator string. Okay. Second, what it tells you, or in other words, you can say it tells you the utilization of insulation material of the string. How much effectively you are utilizing the insulation material of the string, that is being given by this string in the efficiency. String efficiency is given as the voltage across the string. Now, whenever you say voltage across the string, please remember it is the phase voltage, because the individual conductor voltage is going to be taken care by this string. So, it is always the phase voltage which this string has to take care of. Is it clear? It is divided by the number of units multiplied by the voltage across the unit nearest to the conductor. So, if I talk about the string efficiency in this case, it is going to be how much? It is going to be V1 plus V2 plus V3 plus V4, which is nothing but the per phase RMS voltage. Number of units 4, and what is the voltage across the unit nearest to the conductor? That is V4 multiplied by 100%. Now you can understand V1, V2, V3, they all are less than V4. So you can say that string efficiency will always be less than 100% for high voltage AC transmission. High voltage AC transmission. Is it clear for everybody? Are you able to follow this? Now I want to improve this string efficiency. Yes or no? I want to improve this string efficiency. Yes? So let us see what are the methods. But before that, let me talk about the HVDC transmission. If you talk about the HVDC transmission, the currents I1 dash, I2 dash and I3 dash, they are not present. They are 0. Charging currents are 0. These charging currents basically they depend upon the time varying electric field. They are because of the time varying electric field. But when you have the direct current transmission, DC transmission, there is no time varying component. So these charging currents are 0. When charging currents are 0, I1, I2, I3, I4 are same. I1 is equal to I2 is equal to I3 is equal to I4. So the capacitance and capacitive reactance is same. So you can say V1 is equal to V2 is equal to V3 is equal to V4. It means every individual insulator disc in this suspension type string is equally utilized. So what is the string efficiency for HVDC? For HVDC, the string efficiency is exactly 100%. Exactly 100%. This is the reason. I hope it is clear, everybody. Just tell me. I'm not getting your comments. Everybody is okay with that? Okay. So we'll see the methods how we can improve the string efficiency, but let us do this question first. Everybody just see this question. I hope you can do this. Very easy question. The moment you understand the concept, the question will become very easy for you. He's saying it should be, I think, let me write it right here, a single phase. Okay. A single phase overhead transmission line is being supported by 3 insulator discs. So number of insulator discs is 4. The potential drop across the top unit and the middle unit are 10 kilovolts and 12 kilovolts. Okay, so he is saying the top unit. So top unit means V1 is given as 10 kilovolts and middle unit is, because there are 3 units, so middle unit is V2, so it is 12 kilovolts. He is asking the ratio of the capacitance between the pin and earth to self capacitance. What is the formula? Formula is V2 is V1 1 plus K. So K becomes V2 upon V1 minus 1, that is 1.2 minus 1, that is 0.2. What is the correct answer? A is the correct answer. Answer highlighted is there, so no problem if answer is highlighted. What is the problem if it is highlighted, beta? तुमने वो वाली बात कर दी कि मुझे वो छोटी बच्ची हो क्या, मतलब ऐसा बोलना पड़ेगा। अरे ठीक है यार, लिख दिया, अब इसमें क्या है, तो डिस्कस ही कर रहे हैं ना हम तो सारा कॉन्सेप्ट, कुछ ऐसा चुरा के छुपा के कुछ ऐसा तो नहीं कर रहे हैं ना। आर यू गेटिंग दिस? Just a moment. Are you getting this or not? Now tell me. Easy question based on formula. Okay? Listen here. listen. अब ज़्यादा उसका मजाक नहीं बनाना. I just said it. Okay? Methods to improve the string efficiency. How you are going to improve? So basic idea is, if you can reduce the value of K, because V2 is V1 1 plus something, 1 plus K, V3 is V1 1 plus 3K plus K square, V4 is V1 1 plus 6K 5K square plus K cube. So if you can reduce the value of K, you can increase, you can say you can reduce the difference or non-uniformity between listen. Non-uniformity between the voltages. Okay. Now what is K? K is dear C dash upon C. K क्या है? C dash और C का ratio. You want to reduce K. K को reduce करना है तो C dash को reduce करना पड़ेगा, C को बढ़ाना पड़ेगा. You have to increase C and you have to reduce C dash. What is C dash? Inversely proportional to length of cross arm. So if you want to reduce C dash, you have to increase length of the cross arm. And what is this C? Directly proportional to the area of the disc, insulator disc. So if you want to increase C, you have to increase the area of the disc. Now there is a problem. What is the problem? Length of the cross arm cannot be 10 kilometers. Length of the cross arm cannot be 10 kilometers. So there is a limitation. Now area of the disc cannot be 1 kilometer. So there is a limitation. It means this method has limitation. This method is not going to give you much effective results, but still it is a possible method. So we are discussing about it. Second, capacitance grading. What is the meaning of capacitance grading? Let us understand. We are saying that instead of using the insulators of same size, we are going to use the insulators of different size, so that the capacitance of different units are going to be different. It is C1, C2, C3, C4. Yes or no? And we are choosing the capacitances in such a way that the voltage across each individual unit is same. So we are putting the condition V1 is equal to V2 is equal to V3 is equal to V4. What is these voltages? It is I1 multiplied by XC1, I2 multiplied by XC2, I3 multiplied by XC3. This is I4 multiplied by XC4. Now you know that I4 is more than I3, is more than I2, is more than I1. Yes or no? This current is going to be more than this. This is more than this. This is more than this. Why? Because some current is going this side now. I4 is divided as I3 and I3 dash. So definitely I3 is less than I4. I3 is divided as I2 and I2 dash. So definitely I2 is less than I3. And I2 is divided as I1 and I1 dash. So definitely I1 is less than I2. It means I4 is greater than I3, greater than I2, greater than I1. So my friend, you can say XC1 is going to be greater than XC2, greater than XC1, sorry, XC3, and greater than XC4. Now what is XC1? It is 1 upon omega C1. So we can say C1 less than C2 less than C3 less than C4. So basic idea is the capacitance or the individual insulator disc which is connected near the conductor Okay, Prakhar, I will tell you. Wait. Just hold on with your confusion. I will tell you. Please wait. Are you getting this or not? And this is very logical. ये तो common sense है. भाई आपको ज्यादा वोल्टेज ब्लॉक करवाना है तो उसकी कैपेसिटेंस ज्यादा होनी चाहिए. Hello. If you want to block more voltage, the capacitance should be high. So the unit which is nearest to the conductor must have the capacitance highest. And as you move away from the conductor, the capacitance is going to decrease. Is it clear, everybody? Yes, everybody. Are you getting that? Then we have, but this method is also not that good. Why? Because having the different capacitance, and for different capacitance you must have different sizes of the insulator disc, it is going to be highly economical. You understand why Parle-G biscuit is, all the biscuits are of same size? Why not one is big, one is small, one is small? Because whenever you are going to produce something in a large quantity, because of the economy of scale, there is a concept in economy that is called as economy of scale. Economy of scale. The unit cost of production becomes very less. So it is not going to be economical. It is not economical. It is not economical. So this method is also not going to give you any advantage. Now I am going to answer Mr. Prakhar here first. What he is asking is very interesting part. And I think maybe other candidates might be having this confusion, but they are not saying anything. Whenever you have any confusion, you must ask it. Oh my God. Okay? Whenever you have any confusion, you always, जो डर गया समझो मर गया, डरना नहीं है. कुछ confusion है तो उसको पूछ लो, उसको मत छोड़ो अगले जन्म में दूर करने के लिए. इसी जन्म में सारे confusion दूर कर लेना. ओके? पता नहीं अगला जन्म इंसान का हो, ठीक है, सांप बिच्छू का हो, किसका हो, तो इसीलिए इसी जन्म में सारे कंफ्यूजन दूर कर लेना. सुनो सुनो, what I was going to tell you, the voltage distribution. Suppose there are 4 insulator units. Suppose there are 4 insulator units. So C capacitances are 4, C dash are 4 minus 1, that is 3. Like this. This is C dash, this is C. Okay. Now see, let us see what is the voltage. What is the voltage? What is the voltage of this point? What is the voltage of this point? I am going to write here. Between these 2 points. I am saying this voltage is V1. Yes or no? This voltage is V1. Yes or no? Yes. Now this point and this point, voltage across them is V2. This point and this point, voltage is V3. This point and this point, voltage is V4. Now suppose, listen here, I want to know, this is 1, this is 2, this is 3. Okay, and suppose this is 4. I want to know the voltage between this point and this point. So it is going to be V1. Yes or no? This is going to be V1. I want to know what is the voltage between this point and this point. So it is going to be V1 plus V2. Yes or no? If I have to write this current, suppose this is I3 dash, this is I2 dash, it is I1 dash, this is I4, this is I3, this is I2, this is I1. Suppose I want to write here, node 3, I want to write KCL. I want to write KCL. So how you are going to write it? I4 is equal to I3 plus I3 dash. Yes or no? What is I4? Please tell me. What is I4? I4, what is the voltage across it? V4. What is the capacitance? Omega C. So it is V4 and this is omega C. What is I3? You tell me what is I3? I3 is voltage across is V3 and what is the capacitance? Reactance? Omega C. Sorry, susceptance. So it is V3 again into omega C. Now what is I3 dash? Listen very carefully. What is I3 dash? I3 dash is the current flowing between this point, node number 3 and the transmission tower. So what is the total voltage coming across this? V1 plus V2 plus V3. V1 plus V2 plus V3. So it is going to be V1 plus V2 plus V3. And what is the capacitive susceptance? It is omega C dash. This analysis is the basis of how you do any calculation, any analysis in the overhead line insulators, especially suspension type string insulator. If you have this analysis, the only thing you have to do is apply the KCL. Okay. Anyways, see the third method, that is the most practical method, that is called as static shielding or guard wire or guard ring. So basically what is done here, suppose this is your live conductor and your guard ring is going to be something like this. The basic idea is that we have to compensate for these charging currents, I1 dash, I2 dash and I3 dash. Okay. So this guard wire is connected in such a way that there is a capacitance coming something like this. Suppose there is a capacitance coming something like this. Okay. It is some capacitance, suppose Cx, Cy and Cz. So what happens? I3 dash is compensated. I3 dash is coming from here. I2 dash compensated coming from here. I1 dash compensated coming from here. So when this I1 dash going is compensated from I1 dash from here, I2 dash compensated from I2 dash coming here, I3 dash compensated from I3 dash coming here. So I can say that I4, I3, I2 and I1 will be same. Yes or no? I3 dash going here, I3 dash coming here. So I4 and I3 same. I2 dash going here, I2 dash coming here. I3 and I2 same. I1 dash going here, I1 dash coming here. I2, I1 same. When the currents are same, when their capacitive susceptance is same, so voltage across them is also same. So V1, V2, V3, V4, all of them, they become same. But generally, we don't go for compensating all the insulator units. Just by compensating bottommost 2 to 3 units, very effective improvement in the string efficiency you can get. Are you getting that? I will just show you. Just give me a moment. If you get a question on this, no need to remember any formula. Formulas are not going to help you. The only thing you do is apply the Kirchhoff's current law. And how you are going to apply, I will tell you. Suppose you are saying, I am compensating this current I1 and suppose this Cx, so current here is suppose Ix, okay. current is Ix. Current is Ix coming here, and this is I1 dash. And I'm saying that Ix at node 1. At node 1. So I'm saying Ix is compensating I1 dash. What is Ix? You tell me. Ix is this guard wire is going to be at a potential V because it is directly connected to the conductor. And what is the potential of this? It is V1. Voltage across this is V1. So capital V minus V1. Capital V minus V1. What is the capacitance? Cx. So it is coming as omega Cx. What is I1 dash? I1 dash is the current going from node 1 to the tower. So it is V1 voltage. It is V1 voltage, and this is omega C dash. Now you tell me, you are saying sir V1, V2, V3, V4 same. So can I write V1, V2, V3, V4 as simply V? And can I write capital V as V1 plus V2 plus V3 plus V4 as simply 4V? Yes sir. So V minus V1, that is 4V minus V becomes 3V. Omega cancelled. This is Cx. This is simply V. V also cancelled. This is C dash. So what is Cx? It is C dash by 3. Can you do similarly for others? If you go for node 2, do the same. Say it is Iy and it is equating or compensating I2 dash. So you will be getting Cy simply as C dash. If you go to node 3 and you say it is Iz compensating I3 dash, then you will be getting Cz capacitance as 3C dash. You can do like this. Just you go for the Kirchhoff's current law and you will get it. Everybody just tell me, are you able to follow this or not? If you have any doubt, you can ask me. Because this year I am having a gut feeling that you may get a question on this 2023. 2023, you will be having a question on this. ठीक है, देखो मैं जो बोल देता हूँ वो सच हो जाता है, और कई बार मैंने ऐसा पहले बोला है जो सच हो गया है. कभी कभार नहीं होता है, ज़्यादातर हो जाता है. ओके, मजाक कर रहा हूँ, लेकिन फिर भी सीरियसली पढ़ना तो सब कुछ है ही है ना. एनीवेज, सी द क्वेश्चन. Very beautiful question, very powerful, very beautiful question. If you know this concept, this question is like a cakewalk for you. Less than 1 minute, you will be able to solve this question if you have the concept. मुझे वो वाला डायलॉग याद आ रहा है, वो एक पिक्चर थी ना 3 इडियट की. बदतमीज है ये लड़का, ऐसा नहीं बोलते बेटा, गलत बात होती है. हाँ, listen. He's saying it's not for, it's 4. It's not for, it's 4. 4 identical insulated discs are connected in the form of a suspension type string insulator. The ratio of shunt and the mutual capacitance, that is C dash upon C, which is K, is given as 0.2. If the total string voltage is 40 kilovolt, then find the string efficiency if only bottom 2 units are compensated. Okay, if the bottom 2 units are compensated by static shielding. Yes or no? See, very easy question. So what is happening here? This is your transmission tower. There are 4 insulated discs. So it is 1, 2, 3, 4, and this is your conductor. This is pin to earth capacitance C dash. It is C dash, C dash, C dash. This is C, 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 C. Now we have the static shielding or guard wire, and he is saying this is at V, this is at V. He is saying only the bottom 2 units are compensated. Bottom 2 units are compensated means what? bottom two units are compensated means what? Let me write it very carefully. Within one go, you will understand. Here current is I4. Listen very carefully. Here it is I3. Here it is I2. Here it is I1. Okay. If it is compensated, then this I3 dash must be coming from here. If it is compensated bottom two units, then this I2 dash must be coming from here. Now you tell me, I3 dash compensated, I2 dash compensated, it means I4 is equal to I3 is equal to I2. It means I2 is equal to I3 is equal to I4. If the currents are same, capacitance is same, capacitive susceptance is same, so can I write V2 is equal to V3 is equal to V4? Yes. What is V2? It is V1 1 plus K. What is K? Sir, 0.2. So it is 1.2 V1. So can you say V2, V3, V4 all are 1.2 V1? Yes. So can you give me string efficiency now? Yes. Total voltage across the string V1 plus V2 plus V3 plus V4, but V2, V3, V4 same. So I'm writing 3 times V2 divided by number of units 4. V4 is same as V2, that is 1.2 V1. Multiply by 100. Final answer. So it is V1 plus 3 into 1.2 V1 divided by 4 into 1.2 V1 multiply by 100. You can find what is the answer you are getting. Everybody just tell me yes or no in the comment section. ये बच्चे कम क्यों होते जा रहे हैं यार? मतलब अब इससे भी अच्छा मतलब कुछ हो सकता है क्या? मतलब और कैसे रिवीजन कराया जाए? इससे भी अच्छे तरीके से रिवीजन होता है क्या? और जो लोग छोड़ के जा रहे हैं ना सेशन, मैं स्टैम्प पेपर पे लिख के दे रहा हूँ, कुछ नहीं कर रहे होंगे, टाइम वेस्ट कर रहे होंगे मोबाइल पे। उनको लग रहा होगा अरे ये क्या यार, ये तो आता ही था मुझे, बट यही जो आता था ना उसी में छोटी सी गलती हो जाती है एग्जाम में। ठीक है ना? अब वही है, कोई चीज फ्री में मिलती है तो लोग उसकी इज्जत नहीं करते, रेस्पेक्ट नहीं करते। Okay, so be very serious. If I can be very serious for you, if I can be this much serious for you, if the whole BYJU'S exam prep team is this much serious for you, why you yourself cannot be little more serious for yourself? Anyways, so this is over. Now we will be starting the underground cable or insulated cable. Are you happy? Underground cable or insulated cable. Last year there was a question, if you remember, 2022 there was a question that was very fundamental question. So maybe it is just a symbol. Okay. Oh my God. So Ashu sir is with us. Thank you so much, sir. It's an honor to have you in the session. So guys, just say hi. Just give a heart symbol to Ashu sir. He is one of my favorite also, not just yours favorite. So just give a heart symbol. Say hi to Ashu sir. Okay. So now we'll be discussing the insulated cable or underground cable. Now, if you talk about the underground cable or insulated cable, I want to ask you a very fundamental question. Very fundamental question I want to ask you. We are talking about underground cable. You tell me what is the difference between overhead line and underground cable? What is the difference between overhead line and underground cable? Can you tell me? Hello, can you tell me what is the major difference between overhead line an underground cable. I will tell you. Suppose this is your overhead transmission line, OHTL, overhead transmission line. It is like this. This is A phase, B phase, C phase. If you talk about the underground cable, obviously 3 phase. So it is like this. This is the cable and these are the cores. This is A, this is B and this is C. Yes or no? अरे यूपीपीसीएल तो तुम टॉप कर जाओगे गुरु. यूपीपीसीएल तुम टॉप कर, यूपीपीसीएल तो ऐसे ही. ठीक है, मजे करो, सुनो. Listen. You see the distance between individual phase conductor is going to be severely restricted when you come to the underground cable. The distance which was going to be about some meters, maybe 4 meters, 5 meters, 6 meters, now it is being restricted to get into one cable only. It means what? It means the geometrical mean distance is severely restricted. It is reduced. Yes or no? What is geometric mean distance? Geometric mean distance is the distance, mutual distance, or the distance, effective distance over which the mutual flux is present. So it is restricted. Now when GMD is severely reduced, what is the consequence? What is the consequence? Listen here. Inductance per phase is 0.2 ln GMD upon GMR. This is millihenry per kilometer. You are saying, sir, GMD reduced, so inductance per phase reduced. Inductance reduced, what is the inductive reactance per phase? Omega L per phase. So this is reduced, so X is also reduced. What about the capacitance per phase? It is 2 pi epsilon naught ln GMD upon R. Once again, this R is like your normal GMR only, but it is without 0.7788 factor. Why? Because if we talk about the capacitance, in case of capacitance, technically we cannot talk about GMR. Because geometric mean radius is all about internal flux linkages, whereas when you talk about the capacitance, you are talking in terms of electric field, and electric field cannot be present inside the conductor. So technically speaking, you cannot talk about GMR for the capacitance. Rather, we are simply writing R, but this R is actually calculated in the same way that you calculate GMR, but without this factor 0.7788. Are you getting this, everybody? Just tell me yes or no. And this is farad per meter. This is farad per meter. Now you are saying, sir, GMD reduced, then this whole thing reduced, then capacitance increased. That is why one student was saying that, sir, capacitance is high. This is the reason why capacitance is high. This is the reason why capacitance is high, my dear friend. If the interviewer is going to ask why the capacitance is high in case of cable, and if you give him this reason, definitely he is going to start crying on your shoulder. You have to control his or her emotions. It is very important. Okay. Anyways, what about the surge impedance? L is reduced, C is increased, so ZC is reduced. What about surge impedance loading? V rated square ZC you are saying, sir, reduced, so surge impedance loading increase. What about stability? What about stability? P is P max sin del. Now what is P max? P max is approximate power angle equation mod V1 mod V2 upon x. X you are saying reduced, so P max increased. Now for a constant real power transferred, if P max increase, sin del has to be reduced for this P to be constant. Sin del reduce means del reduce. Del reduce means what? You see the approximate power angle curve. If you see the approximate power angle curve, this is the border line. This is the India-Pakistan border. Del is equal to 90 degree. This is stable. This is unstable. Now, if you are operating at a lesser value of del, if you are operating at a lesser value of del, suppose this is del 1, now this is del 2. So there is more stability margin, more space for the system to remain in stability. So we are saying stability is also going to be increasing if you are going to use the underground cable. Is it clear, everybody? Just tell me yes or no in the comment section. Yes? मजा नहीं आ रहा है. कुछ लोगों को ऐसी फीलिंग तो नहीं आ रही है, मजा नहीं आ रहा. यही सब आएगा एग्जाम में. Anyways, so let us see the basic construction of underground cable or insulated cable. See, basically if you see, this is the core conductor. Now core conductor is going to have the main current flowing in the core. And this insulation across, this is going to be cylindrical, is going to be different layers across the core conductor. So basically there are 5 layers. Now you can make your own logic how you remember this. When I was a student in BTech, I used to remember it by very funny things, like I used to say, Sab apne bed mein idhar se aao. So it is very funny how you make things, but 2006 I made this and still I am remembering this, because if you keep on memorizing things in this way, it's funny also, but don't tell this in the interview room. Okay, don't tell this that Ashutosh sir was saying सब अपने बेड में इधर से आओ, तो पता चला मुझे ही बदनाम कर दो तुम लोग. Okay, so there are different purposes for this serving, armoring, bedding, metallic sheath insulation. Let us see what is this serving stands for. Now serving is basically, it is a low grade insulation. Why? Because this is the outermost layer. Outermost layer, तो काय को खर्चा करना है इस पे? Outermost है ना, काय को खर्चा करना? You don't need to spend much money on this because this is the outermost cover. So the basic purpose of this serving is to protect the inner layers and the conductor from the outer environment. That is the reason it is a low grade insulation. Its purpose is to protect the core and the inner layers from the nearby conditions. Then we have the second layer is armoring. Armoring, you remember various Bollywood movies, people going for wars in the earlier times. So they are wearing some steel kavach kind of to protect themselves. Yes or no? तो कोई चाकू मारा ऐसे, तीर मारा तो बच गए. तो वैसे ही कुछ हो रहा है यहाँ पर. Same thing is happening here. Armoring is basically, it is a steel tape to protect or to provide the mechanical strength to the cable. Third layer is bedding. Now bedding is very important. It is made of jute or hessian. Hessian is nothing but वो जिससे रस्सी बनती है ना, उसी का कुछ refined quality समझ लो. वो जो नारियल का जूट होता है, ठीक है ना, जिससे रस्सी बनती है, तो वैसे ही कुछ होता है. It's a form of, you can say, jute, which is also called as hessian. It is basically there to avoid the moisture. And the last one is metallic sheath. Now metallic sheath is the most important part. It is made of aluminium or lead, and it reduces the radio interference with the nearby telecommunication channels. Nearby telecommunication channels. Now let us talk about the calculation of insulation resistance. So when you talk about the resistance, there are basically 2 types of resistances which you can observe in an underground cable. The first one is the resistance in the path of the main current. This is called as the resistance of the core. Are you getting this? There is another resistance which is coming in the path of the leakage current. How leakage current is present here? This is core. This is metallic sheath. Okay. and this is at potential V. This is at zero potential. So leakage current is like this. Leakage current is like this. Can you observe? So the resistance which is coming across in the path of this leakage current, this is leakage current path. This is how we define as the insulation resistance of the cable. It is in parallel. You can see here as a shunt branch. So last year there was a question, I don't remember the exact data, but I will just give you the idea behind that question. Because if it is repeated in other exams, because people are sitting for UPPCL also. So my best wishes to all of you. Okay. So it was something like there were basically two cables. There were two cables. So one cable was represented like this. This was our core. This was our insulation, first cable. And there was another cable. This was our core 2. If you remember it, our insulation 2. And the question was saying, if these two cables are connected in series, then what is going to be some ratio they were asking, the ratio of equivalent core and insulation resistance, something like that, okay? So you can understand by the equivalent circuit, this R core is going to be directly added because they are connected in series, and R insulation is going to be in parallel. So it was approximate representation, okay, approximate representation. Anyways, so let us talk about the insulation resistance, calculation of insulation resistance of the cable. So what is the expression for the insulation resistance of the cable? R insulation is rho insulation upon 2 pi L, it is ln capital R upon small r. Okay, I will not go to the derivation part. You can see the derivation if you don't remember it. The most striking feature of this insulation resistance is that generally if you talk about the resistance, how you write resistance, it is rho L upon A. Yes or no? So more is the length of the conductor, more is the resistance. This is how we understand resistance normally. But you be very cautious when you talk about the resistance of the insulator, insulation resistance, because here this relation is not valid. Here the insulation resistance is inversely proportional to the length of the cable. You have to be very cautious. Okay. Just do this problem. I think you can do it. Everybody just do this problem. Everybody just do this problem. Simple formula base, yeah. What the question is asking, let me tell you. Just give me a moment. Just give me a moment. Yeah. See what the question is saying. Very easy question. He is saying there is a single core cable has a conductor diameter of 1 centimeter. So this is core conductor, okay, and core conductor diameter is given. Core conductor diameter is given as 1 centimeter. And the insulation thickness is 0.4 centimeter. Insulation thickness is also given. This is the insulation thickness. This is given as 0.4 centimeters. Now the only thing you have to find here is, very direct, very easy question. The only thing you have to find here is these two values. What is this radius and what is this radius? This is capital R, this is small r. So small r is going to be 0.5 centimeters. And what is this capital R? This is going to be 0.5 plus 0.4, so total 0.9 centimeters. Okay, so you have to write the insulation resistance, rho insulation upon 2 pi L, ln capital R upon small r. Just put all the values, you will get the answer. And just take care of the units, take care of the units. So I think you must be getting A as the correct option. Is it clear? You have to change this 3 kilometer into the meters. And this ohm centimeter, so change it into the meters. Take care of the units. Now, very classical question for underground cables. Very classical. You all must be able to do this question. Just tell me fast. You all must be able to do this question. Yes or no? The only thing you have to remember for insulation resistance is that it is inversely proportional to the length of the cable. Length of the cable. So for 10 kilometer he is asking what it will be for 100 kilometers. So just product is going to be constant. R insulation multiplied by L is constant. So this is what you have to apply here. So 10 multiplied by 1 is equal to 100 multiplied by R insulation. So R insulation is 0.1 mega ohms. Is the answer. Yes? अरे भैया ये 0.1 होगा ना. तुम्हारे जैसे बच्चों की वजह से ही बेटा आजकल अच्छे टीचर सुसाइड कर रहे हैं. Is it clear? Distribution of electrostatic stress in the cable cross section. Now see, when you talk about the underground cable, the expression for electric field stress at the surface of conductor you can write as the general expression. First I am giving you. It is, this is at the surface, or let me, first I will give you it for the overhead transmission line, okay, for overhead transmission line, so that you can relate it. I got. Yes. So the expression in case of overhead transmission line, the electric field stress at the surface of the conductor is given as V phase upon GMR ln GMD upon GMR. Very important formula. But the expression that you are getting here is at a distance x, where x is in between R and capital R, okay? Somewhere, suppose a radial distance x if you are finding. So this Ex is given as V phase divided by x ln capital R upon small r. This is the general expression where x varies from small r to capital R, okay, small r to capital R. So if I want to know at which point in my underground cable I will get the maximum electric field stress. So please understand, this is operating at potential V. So electric field stress at the surface of the core is going to be V upon small r ln capital R upon small r. What is going to be the electric field stress at the sheath, surface of the sheath? So this is going to be V upon capital R ln capital R upon small r. If you see the ratio, if you see the ratio of both of these, you can understand that E small r upon E capital R is capital R upon small r, which is greater than 1. So very easily you can understand that the electric field at the surface of the core conductor is going to be maximum. Is it clear? But suppose this we are saying is the electric field at the surface of the core, and this is the maximum one. But I want to minimize this value. I want to minimize this value. Why? For most economical radius. What is the meaning of this? The most economical radius means what? If this maximum value of electric field stress at the surface of the core conductor can be reduced, then less amount of insulation is required. Yes or no? Then amount of insulation required is less. Yes or no? It means cost is going to be less. So I want the minimum of this maximum value. For that purpose, the condition that you are getting for minimum of electric field stress at a distance r, the condition is capital R upon small r is E. Capital R upon small r is E. And this radius small r, which is capital R upon E, this is called the most economical radius. This is called the most economical radius. Is it clear, everybody? It's okay, don't worry. I was just... So, R should be greater than or equal to this capital R upon small e. Okay? Anyways, just see this question. Very interesting question. Based on the same concept, the most economical radius concept. Just see this. Now I am going to take 2 atoms of hydrogen and 1 atom of oxygen. If you want, you can also take a little bit of it. Okay. So very easy question. The condition he is asking is determine the economic overall radius. The moment you talk about the economy, it means you are asking me to put the condition capital R upon small r is E. Yes or no? Now you see, he is talking about the metal sheeted for a working voltage of 85 kilovolts and the dielectric strength of the insulating material is 65 kilovolt per centimeter. What is the meaning of dielectric strength of the insulating material? Dielectric strength means it is the maximum amount of electric field stress that it can handle effectively. Yes or no? ज्यादा से ज्यादा कितना इलेक्ट्रिक फील्ड स्ट्रेस हैंडल कर सकता है, दैट इज इट्स डाइलेक्ट्रिक स्ट्रेंथ. उससे ज्यादा इलेक्ट्रिक फील्ड हुआ, देन डाइलेक्ट्रिक ब्रेकडाउन इज गोइंग टू हैपन. सो यू राइट E R as V upon small r. This ln capital R upon small r, this will become 1. Because when R by R is E, then ln E becomes what? 1. What is ER? ER is given as 65 kilovolt per centimeter. This is equal to voltage is 85. divided by R. Just solve R. But he is not asking you R. This is the most economical radius. See this. अभी मैंने कुछ दिन पहले बताया था अपने सेशन में, आपने ध्यान नहीं दिया, फिर से बता रहा हूँ। इसीलिए इंसान का पढ़े लिखे होना बहुत जरूरी है। गंवार आदमी को हर कोई बेवकूफ बना लेता है। इंफॉर्मेशन टेक्नोलॉजी एक्ट सेक्शन 66A पनिशेबल ऑफेंस है, अंदर हो जाओगे गुरु। किसी भी इंटरनेट सोशल मीडिया पे कुछ भी इस तरीके का गड़बड़ करोगे, और बच्चों के साथ ऐसा नहीं करना चाहिए, बट this is not the right platform for you. You can go to any other platform because we are doing very serious business over here. Okay, so be very cautious, take it very seriously. If you are here to learn something, you are most welcome with open arms. But if you are here to create nuisance, then it's not good for you. Perfect. A is the correct option. He is not asking you small r, he is asking you the overall economic diameter. So, you know, capital R upon small r is E. R you know. So, can you tell me what is capital R? Yes. But he is not asking capital R. He is asking overall diameter. Overall diameter means 2R. You must be getting A as the correct option. Is it clear, everybody? Just tell me yes or no in the comment section. What you're asking R by R. You understood the concept? Who is this? Any doubt you can ask me. Okay. Capacitance of single core cable. You can understand the direct formula. You can remember 2 pi epsilon naught epsilon r ln capital R upon small r. That's it. It's like the formula you must have read when you, Ashu sir must be dealing with the line constant calculation. Instead of GMD upon R, it is simply capital R upon small r. Okay. Same formula you can use here. This is the capacitance coming across the core conductor and the sheath. Okay. Is it clear? Now let me just talk about the 3-phase underground cable. Just give me a moment. Okay, so I will be talking about the 3-phase underground cable now. Three-phase underground cable, you have two types of constructions. When the voltage is less than 11 kilovolt, then you have separate cables for A phase, B phase and B phase, A phase, B phase and C phase, A, B, C. Now, when the voltage is more than 11 kilovolt, you have this type of construction, only one cable and there are 3 cores like this. This is A, this is B, this is C. Okay. So, we are not interested in this construction because this already we have discussed. So, individual phase is going to act as a single phase underground cable. So, we are not interested in that. We are interested in the second category when there is single cable and there are 3 cores inside this. The first thing is we are going to understand that how we are going to model it in the electrical equivalent circuit. Okay. Electrical equivalent. But one more thing, one more input I want to give you. I forgot it. Yeah, this we can talk it later also. We can talk it later also, but better if we do it here. That is the charging current. You may get a question on charging current this year. Very high possibility. So you may be getting the question on charging current. Charging current you must be writing as, we are always write charging current in terms of per phase. Okay, we always talk about the charging current in per phase only. Okay. So this is defined as per phase voltage V multiplied by 2 pi f C. And no need of writing per phase because it is single phase only. So this is how you write the charging current. Okay. Is it clear? Now we are interested in three-phase cable having three cores, something like this: A, B, C, A, B, C. How we are going to represent it in the equivalent electrical network? So we are going to use again two capacitances. One capacitance is the capacitance between any two individual cores, that we are calling as CC. And another capacitance between the sheath, this is metallic sheath and any of the core, that is CS. This is also CS and this is also CS. And this is grounded. Okay, this is grounded. Now, for this three-phase underground cable, the most important thing that they are asking is that what is the per phase capacitance of this three-phase system. Okay, so how we are finding the per phase capacitance? Just see, I am going to convert this delta into star. So you can convert it like this. Okay, so this is A, this is B, this is C, A, B, C. This delta I am going to convert into star. So when you go for delta to star conversion in case of resistance, it becomes R by 3. But when you are doing it for the capacitance, inductance or resistance, when you are going from delta to star, it becomes 1 by 3. But in case of capacitance, it becomes 3 times. So if this is the neutral point, this is going to be 3cc, 3cc, 3cc. This is CS, this is CS, and this is CS, and this is grounded. And this is the neutral point. This is the neutral point. Now understand, in case of a balanced system, this is at 0 volts, and in case of a balanced system, this neutral point is also going to be at the 0 potential. So I'm going to just reconfigure this. How? Like this. What I'm going to do is, first you have these capacitances between the sheath and the core. Sheath and the core. This is CS, this is CS, this is CS. Now what I'm going to do is, this point from the neutral I'm going to take and I'm going to connect it to the sheath, because sheath is also at the 0 potential, this is also at the 0 potential. It means this 3cc is going to come in parallel with CS. This 3cc is going to come in parallel with CS. Yes or no? This is A, this is B, this is C. Now you tell me the per phase capacitance. The per phase capacitance is simply going to be 3cc plus cs. 3cc plus cs. But there is a problem. What is the problem? We don't know what is cc and cs. So when we don't know something, what we do? We do the experiments. Yes or no? So when we don't know anything, we do the experiments. Okay? So let us see experiment number 1. Let us see experiment number 1. तुम लोगों में से किसी को कुछ जल्दी तो नहीं है घर जाने की? Because officially the time is going to be over around 8, 6 to 8. तो किसी को जल्दी तो नहीं है घर जाने की? कितने लोग कह रहे हैं कि सर कंटिन्यू करिए, मजा आ रहा है? कितने लोग कह रहे हैं कि सर बाद में देखेंगे, और भी काम है घर में, धनिया नहीं है घर में, धनिया लाना है, सब्जी में धनिया नहीं पड़ेगा तो मजा कैसे आएगा? How much we can continue? Can we continue for 1 hour? How many of you are saying 1 hour, sir, we can continue? 2 hours? Okay. So 5 hours we are going to continue from now onwards. Is it okay? 5 hours is okay for you? Anyways, come here. So experiment number 1. Okay, I am joking, don't worry. See, experiment number 1. What you do, you connect any 2 cores to the sheath and measure the capacitance between the remaining core and the sheath. देखो सुनने में बहुत बड़ा लग रहा है, इतनी बड़ी चीज नहीं है. 3 कोर थे, 3 में से 2 कोर को आपस में 2 कोर को शीथ से कनेक्ट कर दिया और बचे हुए कोर और शीथ के बीच में कैपेसिटेंस इंक्लूड कर लिया. व्हाट डज इट मीन? नजारा कैसा है? नजारा अगर है आपके दिमाग में तो आप कर ले जाओगे. ये है ए, ये है बी, ये है सी. ओके, सो this is something like this. As usual, in the statement of the experiment, he is saying connect any 2 cores to the sheath. Connect any 2 cores to the sheath. Suppose I am connecting B to the sheath. So when you short circuit, when there is no potential difference, so there is no capacitance. So the capacitance between B and sheath is gone. Voltage gone, capacitance gone. There is no meaning of capacitance without voltage difference. So when it is shorted with the sheath, this capacitance gone. C is also shorted because 2 cores we have to short or connect to the sheath. This capacitance is also gone. Now B and C are at the same potential of the sheath. So B and C also shorted. So this capacitance is also gone. This capacitance is also gone. Now he is saying, sir, measure the capacitance between the remaining core and the sheath. Okay. This is CS. This is CC. This is CC. Now if you look into this, from here, what you will see, just see my hands. This point, this point, this point, this point. What is the first thing you are going to see? CC, CC, parallel, CC, parallel, CS. So you are going to have C1 as, suppose the capacitance you see from this is C1. So C1 becomes CS plus 2CC, equation number 1. Able to follow this? Experiment number 2. Experiment number 2. Experiment number 2, you connect all the cores together and capacitance is measured between any of the core and the sheath. Connect all the cores together and measure the capacitance between any of the core and sheath. इसमें क्या कर रहा है, तीनों कोर्स को आपस में जोड़ दे रहा है और किसी एक कोर और शीथ के बीच में देख रहा है कितना कैपेसिटेंस है, इसको बोल रहा है C2. इसमें नजारा कैसा है? Suppose this is A, this is B, this is C. These are the capacitance. Okay. So this is A, B, C. He's saying all the cores are connected together. All the cores connected together means A and B shorted, so capacitance gone. B and C shorted, so capacitance gone. C and A shorted, so capacitance gone. It means all CC capacitances are gone. This is CS, this is CS, this is CS, and he is saying to measure the capacitance any of the remaining any of the core and the sheath. This is C2. Now you tell me how you can get the PDF of this class. Very important and fundamental question asked. The first fundamental question asked in this class. Thank you, Mr. Ashok. If you want the PDF of this session, then you can go to my personal Telegram channel on BYJU'S exam prep, that is Electrical by Ashutosh Saxena. Electrical by Ashutosh Saxena. Okay. Yes, Sanket, you are right. Perfect. See my hands. This point and this point. What is the first thing you are going to see? CS in parallel, CS in parallel, CS. So 3cc. So C2 becomes 3cc. Equation number 2. Now you understand. From here you can get what is CC. It is C2 by 3. Put this value in the previous equation. Okay. So CS already, sorry, it is not CC, it is CS, sorry. This is CS, okay. So what is CS? C2 by 3. Now just put this in this equation. So what is the CC? CC is going to be C1 by 2. Yes or no? C1 by 2 minus CS by 2. Now C1 you know, because C1 you have achieved out of the experiment number 1. So C1 you know. Now put the value of CS. What is CS? CS is C2 by 3. So it is C2 by 6. So you can apply these two formulas. But I would never suggest you to remember the formulas for these type of problems, because anytime they can get a little twist in the problem and you have to go with the fundamental way, the way I am doing it. Okay. Whatever connections are given, make the connections, see the equivalent circuit, see the capacitance you are having. From there you can get it. Anyways, so I have experiment number 3 also for all the lazy people in the house. Any lazy people in the house? Who do not want to do this much calculation? So direct. So I will give you one example with all due respect to all the religions. when Buddhism and Jainism were flourishing as two distinct, listen, two distinct religions from the 6th century BC, slowly Buddhism got little more, you can say, it is spread little more with a more speed than the Jainism. Why? Because Jainism is very strict philosophy is there, and there are a lot of punctualities, discipline you have to follow, whereas Buddhism is little smooth in that way. Now, over the years in any religion, so there are some branches. People try to take different paths, different courses. So this philosophy of Jainism, it got bifurcated into Heenyan and Mahayana. Mahayana were those people who went above the India countries to spread the message of Bhagwan Mahavir. And Heenyan, they went below the India, what are the countries in terms of geographical coordinates I'm saying. Over the period of years, when there were some, we can say, where there were some more branches coming, so there was one more branch, that is Vajrayana. Okay, so it's like a shortcut to the salvation, Vajrayana. So this method is like Vajrayana. Anyways, thank you so much. So listen, experiment number 3. Connect any of the core to the sheath and measure the capacitance between remaining cores. तो बेसिकली क्या करना है, किसी एक कोर को शीट से कनेक्ट कर देना है. Listen बाबू, ABC. Okay. So, what I was saying, yes. He is saying one of the core is connected to the sheath. Suppose C is connected to the sheath. So this capacitance gone. Whichever core is connected to the sheath, capacitance is gone. And now he is saying the capacitance is measured between the remaining two cores like this. This is C3. So what are the capacitances available now? This is CS, this is CS, this is CC, this is CC, this is CC. Now I am going to do something like a magic. Okay, I am going to do something like a magic. So मेरे हाथों का मूवमेंट आपको ध्यान से देखना पड़ेगा, नहीं तो आपको लगेगा जादू है. जादू नहीं है, हाथ की सफाई है. So some more I can say atoms of hydrogens and oxygens. What I was saying is, now see, what I will do is, see, I am going to separate this connection. This is short circuit, na? So whether you connect it like this or connect it like this, it is same. Hello? I am going to separate these two connections. If you separate these two connections, let me make it a little more clear. I am going to separate these two connections. Now this CC and CS will come in parallel. This CC and CS come in parallel. This CC and CS come in parallel, and this CC CS parallel, CC CS parallel are in series. And this total combination is in parallel with CC. I hope you understand the magic. So what is C3? Just see here. C3 is Cc plus Cc plus Cs divided by 2. Cc plus Cs in series with Cc plus Cs, so 1 by 2. In parallel with Cc, so this is. So if you write it, simplify it, it becomes 2Cc plus Cc, 3Cc plus Cs divided by 2. Now you tell me, you tell me, what is this? This is nothing but per phase capacitance, that is nothing but 2 times C3. So the moment you listen this statement in the examination that one of the core is connected to the sheath and the capacitance C3 is found between the remaining 2 cores, directly multiply by 2 and put the answer. Is it clear, everybody? So this is all about 3-phase underground cable. Now let us talk about the HVDC transmission. Is it clear, everybody? Very less comments, no problem. HVDC transmission, let us start. So HVDC transmission, why we are doing HVDC transmission? Understand the logic. Generation can we do in HVDC? Can we do generation in HVDC? No. Generation is only possible in AC. Why? Because DC generators at this much power will become very difficult to manage because of the commutation. Okay. Just give me a moment. Okay. So because of the commutation problem and DC not going to be that much suitable, we are only going for AC in case of generation. If you go to the loads in terms of final consumption of the electric power, that is also in AC, because most of the time it is in AC, because for so many years our loads have been modeled in terms of the AC power, and it is very difficult to suddenly, we cannot say like that tomorrow onwards all the loads which run through AC are not a legal tender and you have to use the equipments or machines running through DC only. So we cannot do like that. So that is the reason we go for AC at the load side also. But in case of transmission and distribution, we can use HVDC. Now after so many years, we started with DC, we went for AC because transformers can only operate on AC, and for power transmission over large distances, we want more and more higher and higher voltages, and we go for AC systems long time back. So suddenly why we are talking about HVDC, there is a significant reason to this. What is the reason? We'll understand. Here you have HVAC, high voltage AC transmission. Again here you have high voltage AC transmission. Now you have a converter station which works as a rectifier. It means it rectifies, means AC to DC. And this is the HVDC line or link or transmission where DC power is going to travel. Now at the load side or the consumer side, there is another converter station which works in case of in the form of a inverter. Inverter means again DC is converted back to AC. So for the power transmission majorly we are interested in the anyways. Okay. So I think let us stop here, okay, because it will take some time and I can feel the energy seeping down. So let us stop here. HVDC we are going to start in the next session, next part. Let me tell you what are the topics I am going to cover. Ashu sir must have told you what are the topics he is going to do. So let me tell you what are the topics I am going to cover. First I will cover HVDC, a small portion. Then I will cover power distribution, a small portion. Then I will cover stability. Then I will talk about unsymmetrical faults. Then I will talk about protection. In protection, I will be talking about circuit breaker and relay both. And the last topic I will be discussing, that is economic load dispatch. So these are 6 topics which I have to cover in the next class. Okay. Is it clear? So next class is going to be literally a big class. I hope you understand. Major topics in this which will take some time is going to be, I think, stability. These two are small topics. Unsymmetrical fault will take some time, okay, but protection is the biggest chapter in this. Stability and protection are the biggest chapter, okay, but we'll see how much time it will take. अरे कुछ नहीं समझ गए यार, पूरा कराऊंगा मैं. समझ क्या गए? See, if you are willing, I can continue right now also. I can continue with the HVDC and power distribution. We can finish it in today's class only. But the way I am getting the response from your side, it looks that because the class is running from 4, so it's not about me because I am just taking the class for last 2 hours, but you are there for 4 hours. So more than 4 hours, I can understand it's little difficult to concentrate. Are you getting that? Yeah, that is the reason I'm saying. So friends, thank you so much for joining me live in the discussion. I hope you enjoyed the session. So these were the things I was supposed to discuss, but in the next class I'm going to discuss along with other things. So thank you so much. Take care of yourself. All my best wishes. Stay connected to BYJU'S Exam Prep and subscribe to BYJU'S Exam Prep for GATE and ESE, Electrical, Electronics, Instrumentation and CS. Download the app and join this Telegram channel also. Okay, you can scan this barcode also. Is it clear, everybody? Thank you. Thank you so much. Now go to sleep and take a deep breath and don't worry about anything. It's going to be good performance. It's going to be a good year, good exam for you. You are going to get good marks, good rank, and you are going to have a great career. Thank you so much once again. Take care of yourself. See you again in the next session. Take care. Thank you.